All right. Hello, everyone. Thanks for tuning in to my FPGA development live stream today. All right, so for those of you who don't know me, my name's Alex Forensic. I am a postdoctoral researcher at UC San Diego. I'm the maintainer of an open source 100 gig NIC / in-network computing platform called Corundum. And as part of my research, I work with FPGAs, optical switches, things like that. Lots of fun stuff. Anyway, the topic of my stream today is going to be the PCI Express interface on Stratix 10 MX FPGAs. So for the research project that I'm currently involved in, we're putting together a test bed that's going to contain a whole stack of these bitware 520N MX FPGA boards. So these contain Intel Stratix 10 FPGAs. And so that means we're going to need to run Corundum on these at some point. Sooner rather than later, probably. So I've had a few people ask, kind of what is the, how do you port Corundum to a, totally new FPGA family? Right now, it basically supports, ultra-scale and 7 series devices. But eventually, we need to support Intel devices and potentially other devices as well. The Ethernet side is not particularly complicated, right? It's just serializers, at least for 10 gig and 25 gig. But the PCI Express side is significantly more complicated to make that work, especially because every FPGA kind of has its own incarnation of that, and they're all a little bit different. So I've been laying the groundwork for this for a while, and today I'm going to, well, maybe not necessarily today, but I'm going to take a crack at it today, and it's probably going to extend over a couple of days, to sit down and figure out what needs to be done to make this run, or to make the DMA engine for Corundum run on these Intel Stratix 10 MX FPGAs. All right, so this is going to be a little bit different perhaps from some of my previous streams, because it's going to be, a lot longer and, more open-ended. So in the future, this type of stream is probably just going to be for Patreon supporters only. So if you find this kind of stuff interesting, please support me on Patreon. The link is below, in the description. Also, if you like the, the open source code that I've been working on, and spend many hours working on it, put it all up on GitHub for people to look at and learn from or potentially use. The support would be much appreciated. All right. So the plan for today is to do a couple of things. We're going to be using this card, which is the Stratix 10 MX development kit from Intel. The part on here is very similar to the one on here. I think it's a slightly different speed grade, but otherwise it's like the same size. It has the same amount of HBM and whatnot. But I have a schematic for this. I don't have a schematic for that because Bitware doesn't release schematics. I just have a manual. So that means if I need to look up something, some little detail, I have a schematic available. So we'll start with this one. The other thing is this card has the dubious honor of being one of the loudest FPGA boards that I have. Whenever you plug it in and turn it on, the fan in here ramps up to like full takeoff thrust, and it's really loud. This one is also pretty loud, but it's a little bit quieter. So just for audio reasons, it's going to make more sense to use this one. All right, well, let's just take a brief look at these boards before we pull up the software and get into the code. All right, so we'll take a look at the bitware one first. One thing I will say about these cards is these are relatively Spartan, right? They don't have a lot on here. I say, as you're looking at the back of the card, it has 500 parts here. The thing is, all of this is just supporting circuitry, basically. So you've got the FPGA that's, well, on the other side of this heatsink mounting bracket. And then you've got some clocking components. These are the SI5341A PLL chips that provide some reference clocks, probably for the serializers. Over here, we've got 4 QSFP28s and a USB connector for USB JTAG. And there's a a management FPGA over here that's used to load the configuration into the main one from, this looks like a pair of QSPI flash chips. And that's about it in terms of the main circuitry on here. Well, there's also a pair of DRAM sockets here. There's nothing installed in these because the FPGA already has 16 gigabytes of HBM on the package. There are a couple of other connectors. On the back of the card, we've got power and then these high-speed connectors, which I think can be used for either I think they can be used for PCIe and Ethernet, whatever you want. And I think depending on the board, there may be an option for a couple of additional connectors, but it might not be available on the actively cooled card because I think I can see the footprint like right underneath the blower. Yeah, so there's not a whole lot to this. The rest of all this stuff on here is just power supplies, right? Power, 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 power. These are power supply controllers. These are all level translators, I think. Yeah, everything else on here is basically just power. Yeah, this card requires a lot of power connectors as well. I think you have to have both power from the edge connector and both of these connectors as well for the card to turn on. Some of the other boards are a little bit more forgiving. Like the Alveo boards from Xilinx, they'll run just fine off of the edge connector alone, just with a lower power envelope, basically. All right, so we'll take a look at this card briefly. This is the Stratix 10 MX development kit. And this one has the version with 16 gigs of HBM. So again, the FPGA is here. And then the rest of this is basically just power. Well, there's a configuration flash here and a management FPGA here. We got PCI Express endpoint connector, host connector, or root port connector. And then on the back, we've got a pair of QSFP28s and a USB connector for USB JTAG. Let me just pop the top off of this real quick. This is one of the more unique FPGA boards that I have because they have this gigantic metal box, and it's actually quite satisfying the way it clips on. Anyway, they have these gigantic, super thick metal plates on the sides. It's a little excessive. Anyway, the FPGA is here underneath the gigantic heatsink. We've got the QSFP28s. We have a single DRAM module here. We've got some component DRAM over here. There's also this connector. I don't know what it's called off the top of my head, but that one I believe can be used to either add some additional DRAM or potentially to add some SRAM. And then there's a JTAG connector over here if you want to plug in an external JTAG cable. Oops. Yeah, there we go. And then the rest of this stuff is just power, right? All of these Intel and Purion power devices. Yeah. So like I said, there's not all that much on here besides, the FPGA, some connectors, and a whole bunch of power supplies. All right. So now in terms of the PCIe interface, the first thing that I'm going to do, once I get this top back on, is we're going to pull up the Quartus Prime software, and we're going to go ahead and generate a PCIe IP core instance and take a look at it just so we have a handle on what all of the what all the interfaces are. All right, so let's go ahead and switch over and take a look at that. All right, let's see. I'm also going to switch. Okay. All right, so I've done a little bit of prep work here. I have a QSF file for this board. You can actually get the board with two different parts. The only difference is the size of the HBM and the speed grade of the part. So we're just going to build this for the board that I happen to have here. Right, so this has all of the connections. Here are all of the PCI Express endpoint connections, including the reset connections and the reference clock. All right, so go to my make file here. And let's see. Oops. Let's see here. This is Quartus Pro settings. All right. Muscle memory. I'm always running Vivado. Let's see. This is fpga.qpf. All right. So that goes ahead and builds the project file. Now I can go ahead and open that up. Let's see here. All right, there we go. Okay, so here is Quartus Prime Pro, and we're going to go ahead and build a PCI Express IP core for this part. And in doing so, we can go through all of the main configuration options and whatnot, make sure everything looks good, and then we can take a look at what the the configuration or what all the internal interfaces look like. And the other thing we can do is test just a bare PCIe IP core on the FPGA. So once I get this core generated, we'll go ahead and build just a bare core, and we'll make sure it enumerates. The reason for that is that the PCI Express IP core handles all of the low-level stuff, right? It handles bringing up the link, and it handles the configuration space, which is responsible for enumeration. All right, so let's go ahead. I need to generate two things. The first one is this reset release IP. I think that's the right one. The parameter editor is quite slow. All right, there we go. I'm going to call this reset release. All right, got to give this a moment. Okay, that looks fine, so I'll go ahead and generate that. Yes, save it. Okay. All right, so while that's doing its thing, I'm going to go ahead and pull up the PCIe IP core. So we'll go, oops, I guess it's going to be PCI Express, not PCIe. Okay. So there are 4 different cores that appear. There is the Intel L or H tile Avalon memory mapped for PCI Express. Then there's the same thing, memory mapped plus for PCI Express. I have no idea what the difference is. And then there is the Avalon Streaming, and that's the one that we're going to use. The memory mapped ones, I believe, have a built-in DMA engine. And then there's the multi-channel DMA for PCI Express. And I'm not sure what that is exactly. So, but what we want for Corundum is the transaction layer core. So that one is the Avalon Streaming core. So we'll go ahead and generate that. All right, so that one's done. Okay, this is going to be PCIe, create, and this one, I'll close that. Okay. Unfortunately, this is probably a little bit hard to read for everybody. Unfortunately, I don't think there's any way I can make this, any bigger. The downside of having a 4K screen, unfortunately. Well, in combination with applications that don't scale for high DPI monitors. This is far from the fastest piece of software ever. All right, I think that's, well, give it a moment. All right, I resized that. There we go. That's better. All right, let's go ahead and take a look at all of the configuration settings that are here. There's not all that many options to choose from. So application interface, can't change that. Hard IP mode. I'm going to set this to Gen 3 by 8. The reason for that is the 512-bit interface is composed of 2 segments. and I don't want to deal with segments for the time being. So we'll just do Gen 3 by 8. Once we get that working, then I can take a look later at getting segments working. All right, so port type, native endpoint or root port. Native endpoint is fine. That's what we want. Multiple physical functions. We just need one function. So, all right. Streaming settings, Avalon streaming settings. Do we need a separate reset output? No. Byte parity, don't need that. Oh, I unchecked that. And what are all these warnings about here? All right, whatever. I'll leave that checked then. Okay, base address registers. So for the example design for the PCI Express core that I have, I generally set up two base address registers, bar 0 and bar 2. All right, and both in 64 bits. So bar 0 is set up for 64-bit prefetchable, and the options are either disabled 64-bit prefetchable or 32-bit non-prefetchable. And then the size, I will set this to 16 megabytes or 24 bits. All right, so that's bar 0. And then I go over to bar 2 and I set this the same way, 64 bits. And let's see, 16 megabytes. Okay. Now the reason I don't use bar 1 is because when you set it to 64-bit mode, it basically consumes 2 bars. So bar 0 will also, you know, take over bar 1, and in this case bar 2 will also take over bar 3. So you set bar 0 and bar 2 to 64 bits, then you can't use bar 1 or bar 3. So if you're doing everything 64 bits, you basically only get 3 bars per PCIe device instead of 6, which, you know, it's not too bad. All right, so that's that. Device identification registers, I'm going to set this to my usual 1, 2, 3, 4. Device ID, I'm going to set that to 1. Okay. Version ID, that's fine. Class code, leave that alone. All right, I'll also set the subsystem ID to 1, 2, 3, 4. And all right, there we go. Okay, so these will show up in LSPCI or whatever. This is what the operating system uses to attach the correct driver. It matches the vendor ID and the device ID, and potentially the subsystem vendor device IDs, potentially the class code. It uses all that information to figure out which driver to attach to a particular device. All right, so PCI Express capabilities. All right, max payload size, that's fine. We want the extended tag field. Don't need function level reset. All right, link. I think this is only really required for the root port side. Port number. Yeah, I think this is if you have, you know, multiple slots, then setting the link number is useful. All right, MSI. We'll enable that and set that for 32 channels. So MSI is message signaled interrupts, and MSIX is like a variant of that that uses a slightly different setup in the configuration space for more or less the same thing. MSI only supports up to 32 interrupts. MSIX supports a lot more. I'm not sure what the limit is off the top of my head. All right, well, I guess the trick with MSIX is the actual vectors and whatnot don't live in the configuration space. They live in one of the bars. So that means you're not limited by the size of the configuration space. You can basically make the tables as large as you like. But presumably there are practical limits on that. All right, slot. This is for root port, so we'll ignore that. Power management. That's not a big deal. VSEC. Oh, this is vendor-specific extended capability. Yeah, don't need that. All right, configuration, debug, and extension. I'll leave all those unchecked. PHY characteristics. Gen 2 de-emphasis. I'm not sure what the correct setting is. I'll leave that at default. VCCR/VCCT supply voltage for the transceiver. There's two options, 1 volt and I guess 1.1 volts. I have no idea what that is. Let me see if I have a let's see what the schematic says about that. All right, this is the schematic for the dev board here, right? This is the Stratix 10 MX FPGA dev kit. You can download this from Intel, so you know, I have no qualms about pulling this up here. So let's take a look here. All right, so here's the FPGA. We got the endpoint connection over here, which is on the transceiver sites 1 CDE. Okay. Here's the power tree. This is why these boards have so many parts on them. Look at all of these power supplies. Ooh, boy. Yeah. That's where all the parts on the board are coming from, just to supply all of these things. So this is, 12 volts for the DDR-T DIMM. This is VCCIO UIB. Not sure what that is. S10 VCC, that's like the core supply. ERAM, PLL digital, VCCT, VCCRR, VCCRL, VCCH, VCCADC. Yeah. This is for the DRAM. This is for the QSFPs. Yeah, lots of stuff on here. Okay. Anyway, what are we looking for? We are looking for the VCCR/VCCT supply voltages for the transceiver. Maybe it's these. That would make sense, but I'm going to try to confirm that. All right, let's see here. If I keep going down, let's find the PCIe edge connector here. I think that's coming up. Okay, here we go. PCIe endpoint edge connector. All right, so this one, all of the differential pairs, this is hooked up to PCIe IP RX on page 22. All right, here's page 22, PCIe EP RX. All right, that looks fine. This is GXBL1D, right? That's what I was saying, 1C, 1D, and 1E. All right. There's no power pins here. Okay, so where are the power connections for these? Gotta be around here somewhere. This is... No, that's not what I want. They're all I/O pins. Oh, here we go. VCC, VCCR, GXBL1C. Yeah, okay, so this is what I want. VCCR and VCCT. So this comes from S10 VCCT GXB and S10 VCCRL GXB. Okay, and I think that corresponds to what we saw earlier. Here's another power tree here. VCCRL. Oh, but these don't say GXB. Let's see, where was that? Where are these driven from? VCC ERAM, VCCRL. Oh, here we go. VCCRL GXB. So that's 1.12 volts. Okay, 1.12 volts, 5 amps. Wait, didn't this say 4 amps? Yeah, 4 amps, 1.12 volts. The schematic is not consistent with itself. Go figure. All right, but 1.12 volts seems to be closer to 1.1 than 1.0, so I'll set that to 1.1. All right. Anything else that I need to do here? I think we're good. I'm going to go ahead and hit the generate HDL button. All right. And then we can take a look at the generated code. So go ahead and save that. All right. Cool. While that's running, let's take a look at the documentation for the IP core itself. Where did I put that? Here we go. All right. So this is the manual for it. And the interfaces should be detailed somewhere. Let's see. I think it's around here. Maybe not. Block descriptions. There we go. All right. So this has all of the pins on this core. You're not going to let me zoom in any more than that? That's annoying. All right. Well. All right. So there's a lot of stuff on here. But most of this is not particularly relevant. It's some of these are for simulation, and some of them are associated with, you know, particular more advanced features. So taking a look at this, we've got the most important ones. We have the Avalon streaming RX and TX connections. So these are going to be for actually moving the TLPs to and from, you know, the DMA engine and other interface components. Below that, we have the TX credit interface that's used to keep track of, you know, how many transmit credits are available for sending stuff over the link. Then we've got clock and reset. These signals are associated with message signaled interrupts. And this one looks like you can actually send or issue MSI interrupts directly from the core. From the P tile on Stratix 10DX, you actually have to generate the memory write requests manually and send them in the TX interface. But this looks like it can generate these packets internally, which is useful. There's also some configuration space connections here. So this appears to be for reporting errors. And then this one is for basically exposing some of the configuration settings from PCI Express configuration space to the user logic on the FPGA. So there's a bunch of stuff in here that we may need to look at. All right, and then we have the configuration extension bus. And I think this is used for if you want to implement your own configuration space structures. I'm not sure if you can override the default ones or if you can just basically add new ones, but that's what it's for. We don't need to do that, so we can ignore that. PLL reconfiguration, we can ignore that. Control shadow. I'm not sure what this is related to. I think it has something to do with SRIOV, but we're not using that. Hard IP status. These are a bunch of data parity error signals, interrupt status, you know, internal state, so LTSSM state indicating, you know, whether the link is working or not. This is, if you're having like physical layer problems, looking at the LTSSM state on like a logic analyzer or something like that can give you a lot of insight as to what's going on there. But if the link comes up, then that's not particularly important. All right, let me take a look at Quartus here. Is it still going? It's still going. All right. All right, and then we have the hard IP reconfiguration. For what we're doing, again, this is not something we need to play with, but this will allow you to change internal configuration settings. And I'm not sure if you can change stuff in the configuration space, possibly. I'll have to take a look at that at some point, probably. This is all power management. I'm just going to leave this thing in the high power mode all the time because, you know, why not? Keep things simple. So I think all these signals can basically be tied off. Then this is the actual serial data interface, right? So this only shows one lane, but you would have, you know, 8 or 16 lanes or whatever there. And then all of these signals are for simulation. So this is, it says pipe interface for simulation and hardware debug. So pipe in this case stands for, oh, what was it? PHY interface for PCI Express. I think that's right. It's a standard from Intel that basically allows you to separate the higher level components of PCI Express from the lower level ones. So the application, you have the transaction layer stuff here. So you're transferring TLPs, and then you have like the PCI Express kind of MAC layer, which takes these the TLPs and packs them and formats them into the physical layer, you know, control characters that get sent down the individual links. And then the PHY is responsible for managing all of the serializers and whatnot to actually send these down the link. So this is kind of the intermediate connection between the MAC layer and the PHY layer. And in this case, you cannot access these signals from the FPGA because these are internal to the H tile. But they are useful for simulation because it's a lot faster to use these instead of to try and actually generate the serial data over the serial data interface here. All right, and what else do we have here? Finally, we got the function level reset interface. So I'm also turning that one off because, you know, less stuff to deal with. All right, so basically the main ones that we need to look at are the TX and RX connections here for TLPs, clock, reset, interrupts, and potentially some configuration space. And then obviously the TX and RX serial data. And then a couple of these unused connections, like for power management, need to be tied off. And basically everything else can just be ignored. Or it's disabled and won't appear. So we'll take a look at what the core looks like when this is done generating. What the heck is going on here? It says done reading input file. All right, well, I'll give it a couple more minutes and see what happens. All right, well, this is what the interfaces to the core look like. So the question is now, what do we need to do next? So hopefully this will finish up at some point in terms of actually generating a core. Let me go ahead and get this out of the way for the time being, and we can take a look at some of the HDL. All right, let me get all of this stuff out of the way. If I need to, you know, redo that later, then we'll try that. Okay. Let me see if it generated anything useful here. I go down to that one. Okay. All right, so here is the Stratix 10 MX code, and we have, I guess it hasn't generated all the output files yet. It's generated a bunch of stuff, but not all the output files. I'm looking for a couple of files here. It generates a one of these inst.v files, and this shows what the actual code looks like that you need to paste into your Verilog. So this one is for the reset release IP, but it hasn't generated one for PCIe yet. So possibly I need to restart something and run this again. Anyway. The focus today is mainly going to be in terms of getting the test benches to run. Obviously, running a real quick test in hardware is useful just to make sure everything is looking good at the board level, but that's not particularly important. All right. So, in terms of what we need to do at a high level, the PCI Express IP cores, kind of the DMA engine and the PCIe AXI Lite master modules, they export a generic PCIe interface. All right, so this is something that I've been working on for a while. This is the PCIe DMA interface module, and this is responsible for communicating with the PCIe hard IP on one side with PCIe TLPs, and then on the other side communicating with an internal RAM that's used to store all of the data that's being, you know, transferred. All right, so the way this interface works is it has one signal for the data and a separate signal for the header. So the header is actually moved kind of as sideband data. And the advantage of doing this is, well, there's several advantages. The first one is that the header and the data are going to be handled basically by two different sets of logic, right? The header is going to be handled by logic that's going to be either interpreting or building the TLP header, and the data is either going to be read or written to, you know, this memory interface. So they're going in two different directions. Putting them on two different signals is not really going to be a problem in terms of the logic, because they're going to be separated anyway. The advantage of keeping them separate and separating them earlier is because this basically gives you a wider interface, right? We now have another 128 bits that can be used for moving data around over the bus. The other advantage is that the maximum size of the TLPs tend to be, you know, a nice power of 2, right? It's either 128 bytes, 256 bytes, 512 bytes, so on. So if we're packing this into a nice power of 2 wide interface, you end up getting, a better throughput. So if we peel off the header, instead of having to insert this, 64 or 128-bit header in front of all these data payloads, and you have to do all the shifting and whatnot, and leave a gap at the end of each frame, you end up getting better throughput. All right, so and the other thing is this also makes things easier to adapt to different FPGA architectures, because this header, from the standpoint of the DMA IP core, is just kind of a normal PCIe TLP, normal PCIe TLP format. And then what we can do is have separate logic which will adapt it and pack it into the actual full TLPs that get sent to the hard IP core over the link. So this is something I've been working on for a while to get this implemented, and in combination with that, I wrote a set of modules here which adapt this to the Xilinx UltraScale PCIe interface. So with this one, we have the 4 streaming interfaces that connect to the PCIe hard IP over here, and then down below we have all of these internal interfaces which will go to the DMA interface. So I've actually split it into 5 interfaces instead of the usual 4 that Xilinx uses. And the reason for that is so you can do the merging between the outgoing read and write requests as close to the PCIe hard IP as possible. And that has some flow control implications. Right, so in this case we've got 2 TLP outputs here. This one is for request packets that are going to the AXI Lite master, requests against one of the base address registers. This output here is for completion packets that are going to the DMA engine. So this is going to be read or write requests. This one is just completions. And then we've got 3 different inputs. This one here is read requests coming from the DMA engine. This is write requests coming from the DMA engine. And this is completion TLPs coming from the base address registers. So basically what happens is you'll get a request out of here that's to read or to write to, well, I guess in this case, if you get a request to write, then there's no response. But if you get a request to read, then there will be a corresponding completion that you have to generate over here. For the DMA engine, you can issue, write requests here, or you can issue read requests here. Read requests that you issue here will eventually result in a completion coming back here. Pretty straightforward. So this module here for the UltraScale devices has 4 modules inside of it that adapt each of these 4 interfaces, right? So the RC is for the requester completion. So this accepts data from the PCIe IP core and converts it to this generic format. RQ, this is for the requester request. This accepts TLPs from these 2 interfaces from the DMA engine and packs it into what's going out to the PCI Express IP core. And same thing on the completer side. This is for handling the completions that are going to be going out on the wire, and this is for handling the requests that are coming in. Now, on the Intel FPGAs, instead of having 4 interfaces, they only have 2, right? They have a transmit interface and a receive interface. So the breakdown ends up being a little bit different. So I have over here the H-tile interface that I've started to put together. This one doesn't have any actual HDL in it yet. This is one of the main things that I need to work on today. Oh, and some of these signals need to be updated as well. Like this one, we don't have that on the H-tile. Well, I'll deal with that in a minute. Okay, so, oops, that should be, oh yeah, PCIe, that's fine, okay. All right, so this one, it has connections to the RX interface and the TX interface on the PCIe IP core. And then on the other side, it has these internal interfaces that will face the DMA engine. All right, and then inside it has two modules, this one handling the receive direction and this one handling the transmit direction. Yeah, not particularly complicated. Well, I guess I don't have anything in here for flow control yet, so I can go ahead and remove this. The P tile has both RX and TX flow control, but for some reason the H tile only has TX flow control. All right, I was just looking at some of this yesterday in preparation. All right, so what we need to do today is basically get these adapter modules operational. And right now they have no code in them, so I need to work on those from scratch. All right, it looks like the generation for the core finally finished in Fortis here, so we can now take a look at what this core looks like. Okay, generate completed with warnings. So I'll hit close there. I will close that. And well, let's take a look at what the core looks like in Verilog here. Let me see. Yeah, okay, so now we have the instance here, and yeah, there are a whole heck of a lot of signals because most of these are just the PCIe pipe connections. Yeah, so let's see here. This is the instance. We got the ref clock, core clock out, hard IP, NPOR, power on reset, in PCIe reset. Yeah, all right, so what I'm going to do is I'm going to take this core, or this instance here, and we're going to put this into this test design that I have. I think I want to go here. Yeah, okay. So this one has, the top level clock connections and PCI Express connections. And I have the reset release instance here, and then also a reset synchronizer. I'm going to go ahead and add the PCIe IP core here. All right. So this is the PCIe hard IP instance. Okay. Now let's start wiring stuff up. So ref clock, this is going to be coming from the ref clock PCIe EP edge P. Right, we can go to that. Core clock out tip. I have nothing to hang off of that right now. Let's see, NPOR. I'm going to do not reset 100 megahertz. Okay. And then we got the reset pin. This comes from the edge connector. That's going to be the S10, that one. Okay. Reset status. Yeah, a lot of these I don't really care about, so I got those two core ready. I need to tie that high. Some more outputs that I don't need. Test in 0, okay, that's an output. Here ST, all right, init done. This comes from the reset release IP. Okay, and now we have the first of the, let's see, the Intel or the streaming interface connections here. So I'm gonna go ahead and clear out some of this stuff. All right. So we've got the ready connection, so I'm gonna tie that high. Oops. All right, start a packet, end a packet. Don't need that. So at this point, what I'm gonna do is just make all of the, clock and reset connections that are necessary, as well as all of the high-speed serial connections. And the idea is to put everything together such that I can load this on the FPGA and we'll see if it enumerates. All right, so there's that. Most of these connections here are just not being used. Okay, so that's for the RX. Now for TX, no start a packet, no end a packet, no data. Not sending anything, so it's set valid and error to low. Ready, we'll ignore that. RX, why is RX bar range all the way down here? I don't know. Anyway, all of those are outputs. Okay. All right, let me go ahead and clear out all of this stuff. Okay. Interrupt interface. Most of these I'm just going to tie again to 0. So there's that. Oops. Get rid of that underscore. Okay. So we've got interrupt request, interrupt acknowledge. That's going to be traffic class. This is the MSI number, interrupt status. MSI. Oh, so interrupt status. That must be for the legacy interrupts. That's 4 bits wide. All right. MSI function number. Also tie that to 0. Int status common. All right. Now we have a bunch of outputs here that are just for, well, the TL config ones we will need later. The other ones we don't need. All right. So now these are for the error interface. All right. Don't need that. Okay. Pipe clock. Don't need that. Pipe rate. That's output. Another output. All right. So now all of this has to do with the pipe. So all of these connections are not necessary. Well, let's see here. I'm going to go ahead and move all of these. Output, output, output. All right, so all the outputs are going to be just removed. And the inputs, I will just tie everything to 0. All right, that's all the outputs. Now for all the inputs. Because these are only used, like I mentioned before, for simulation. All right, so get rid of all that. Okay, cool. Well, that is input. All right, and now we have the actual high-speed serial connections here. So these need to be wired up to the board level connections. So in this case, only using 8 lanes for now, right? So I will do 7 to 0 here, and I have the TX connections here. All right, let's see, TX out. That's going to be here. And I can copy these over here. All right, and then again, RX connections here. PCIe IP, all right, RXP. There we go. And then I can get rid of all of this. All right, almost done here. Let's see, we got a bunch of outputs. There we go, that goes away. And then a bunch of inputs here. These are just for power management. And I can just tie all those to 0. All right. And I got a couple of other comments to clean up here. All of these can go away. And then I think we're good to go to try building this. All right. Go ahead and save that. Right, so we got the, I gotta align these. Okay. All right, there we go. Now I'm gonna try building that. And we'll see if that works. All right, yeah, go. All right. I'll let that run over here. And we're gonna take a look at some of the simulation components that are necessary for testing these shim pieces. Hopefully this will work. If it doesn't work, then we'll revisit that and adjust as necessary. All right, so that's going. And once this is built, then I will go ahead and pop the card in my development machine and we'll test it out. All right, so going back to the H-tile interface code. In order to test this, what I need to do is have a simulation module working for the streaming interface here. Well, and a lot of these other sideband signals. I think I'm not sure about for the transmit flow control credits. We can skip that for now. But oh, lots of red. That's not good. What happened? 20 errors, 97 warnings. Oy, that's a pain. What is Quartus unhappy about? Oh, I think I edited something. Full core, where was that one? PCIe H-tile. Ah, okay. I'm just going to comment this out for now. That file's not even being used. I don't know why. Well, I guess it's included in the project, but it's not being used for anything. So we'll circle back around to this one once I actually have some stuff working in simulation anyway. All right. Okay, so that is running. Hopefully it doesn't crash again. That crashed pretty quick though, so that's good. Fail early, right? That's the way to go. Okay, so let's go back to the shim here. Right. So in order to test this in simulation, we needed a simulation model for the PCI Express hard IP core itself. So I've been working on one of those in cocotbext-pcie. So this is the simulation model that, well, this is the test bench for it. This is the H-tile model that I've been putting together. And these models are broken down into a couple of pieces. There is an interface.py file here that's responsible for, you know, kind of the main streaming interfaces. And then there is the hard IP core model that makes the connection to the core simulation framework, as well as implements a lot of the other ancillary interfaces. All right, so this one, this has some bus objects that correspond to all of the signals. Right, so this is data, startup packet, end of packet, valid, ready, header, or error. Sorry, this doesn't have header in it. And some helper methods. This is, let's see, the H-tile PCIe frame, which, let's see, I guess this encapsulates, right, so what this does is this will take a PCIe TLP and convert it into just bare D words that gets sent over the link. So this one's not doing much more than that. For the P-tile, it would also have to peel off the header and put that on a separate field. And then H-tile PCIe transaction, this is just all of the stuff that ends up in these buses here. And then the H-tile PCIe base, this one is stuff that's common to both the transmit and receive direction, right? So this does, it checks all of the signal widths and a few other things. And then we have the source and the sync code, and these are responsible for actually generating the Avalon streaming protocol for the transmit and the receive direction. So, well, not so much for the transmit and receive direction, but it can source or sync either the transmit or receive traffic. So you can use it on either to simulate the hard IP core or to, you know, simulate the user logic, if you will. Oh. Fortis is not happy about something. All right, what is the problem now? Same file. Dang it. I just need to comment out even more. Let's see. What line was that? 492. That's down here. Yeah, oh, because those come from the top level. Oh, it's just those two. All right, cool. Okay, we'll let that run. This is why I like doing the stuff in parallel. Sometimes I need to fix a bunch of little minor things in order to get, you know, the tools to be happy. And then they take a while to actually do their, you know, build process afterwards. All right, so this is looking... All right, so this code I think works, and I have a test bench that runs some basic tests. Oh. And Quartus failed again. Let's see, what is it unhappy about this time? All right, you know what? I'm just going to comment out basically everything in that file, and we'll bring it back later as necessary. All right, there we go. Actually, be on the safe side. Comment everything. All right. Okay. Right, so that's the interface. this is then the H-tile model. So this one has a couple of components to it. This is basically an object for the PCIe functions or endpoints, and this one adds all of the configuration space structures at the offsets that match whatever the documentation says, basically. Oh, did I rerun this, or oh, did I? Looks like the same errors. I thought did I not save the file? I did. All right. I will take a look at that in a minute. Okay. Anyway, so this one is it's basically kind of a generic template for, you know, each function. So if you just have one function, then it instantiates one of these. If there's multiple functions, then, you know, multiple of these will be instantiated for each of the physical functions on the device. All right, so this is a model of the PCIe device. All right, so this is still unhappy. All right, there's something else wrong in that file. Oh, 49. Okay. Oh, I see. What am I going to do about that? Oh, so this should just be the TX sequence number with, again, TX, okay. Okay, PCIe tag count, that seems fine then. And seg empty width, oh, that one needs to be copied from a different file. Seg empty width here, all right. Okay, let's see if it's happy with that now. I'm not sure why it was complaining about stuff further down. It was like complaining about signals down here that were missing and not stuff at the top. Strange. All right, well, let's see if it runs this time. Okay, so where was I? This module here in Python is the H-tile PCIe device. So this one, it has, you know, all of the top level signals here. Although there are a couple of places where you have to do things a little bit differently. For the transmit and receive interfaces, you have to create, you know, these bus objects and pass those through. You don't pass through the individual signals. All right, so those are all the signals, right? We can see the hard IP reconfiguration, configuration extension bus, configuration output, yada, yada, yada. Okay. Then all of this checks the signal widths and potentially initializes them to some initial value. And let's see, what else? This prints out kind of a summary of the configuration. There's some asserts to make sure everything looks okay. All right, and then we have the connections to the PCI Express infrastructure. So we've got upstream receive. If we get a TLP from, you know, the simulated link, then we have to pass it through. So depending on what it is, if it's config type 0 or type 1, then those get handled appropriately. If it's a completion or, you know, some sort of request, then this gets converted to an H-tile frame and handed off to the user logic, basically. So this is where it gets sent out of the internal interface, you know, into the HDL design. Right, so we have this for completions, for IO reads and writes, and for memory reads and writes, and these need to be handled a bit differently because, you know, for the memory reads and writes, you have to go look up what the bar is. Yeah, okay, so where's bar come from? Yeah, okay, so you do match bar based on the address, and then you pass the bar number in a sideband signal. So this is where that is generated. And for IO operations, for whatever reason, instead of specifying what the bar is, Intel has the rather silly idea of saying it's bar 6, which is kind of annoying because if you have two IO bars, then you can't differentiate between the two. But I guess the thing is, why would you ever use, more than one IO bar? Or for the most part, why would you use an IO bar at all, period? So anyway, so that is kind of the internal connection for handling TLPs that are coming from the simulated PCIe infrastructure and going into the HDL. All right, then we have some reset handling stuff. Here's some code to handle the flow control credits. So for the posted header credits, posted data credits, non-posted header credits, and completion header credits, all of these are basically just exposed to the user logic. And then that configuration output interface, this uses kind of a TDMA scheme to output a bunch of internal information. So basically what this does is it cycles through several groups of information. And then in the user logic, you can pull out, whichever one you need. So this has like the MSI message data, the MSI message address, the mask bits, let's see, the max payload size and read request sizes, busmaster enable bit, all of this stuff comes out through this interface. So there are, I guess, some advantages to using kind of this TDMA scheme, because you can just, latch it where you need it. But it does require a little bit of additional code to make that work. All right, so this is what generates that. And then, let's see, I have a test bench here for actually testing the model. And what this does is it instantiates a root complex, it instantiates the PCIe p-tile device. Let's see, it connects it, sets a bunch of initial values. And then what this does, it sets up a couple of the source and sync modules internally that it can use for interfacing with the IP core or interfacing with the simulation model to make sure that it's doing the right things. Now, I mean, I guess this is not a complete test, but it is enough to kind of exercise it and make sure everything works. All right, so this sets up a couple of bars that are used for the tests, and let's see, what else is done here? Right, so wait, where are the bars set up? This one is just allocating regions. Oh, that's where the bars are set up, right? So we got 3 different bars. One is the IO bar, one is a 64-bit memory bar, and one is a 32-bit memory bar. So yeah. All right, so this code here handles completions that are coming from the simulation model, and basically what this is doing internally is implementing, all of the kind of standard DMA operations. So there's a bit of duplication here between some of the stuff in the PCIe IP core, or not the PCIe IP core model, but the PCIe simulation framework. All right, so this handles the RX TLPs. Let's see, so I don't have the IO stuff implemented. Mainly I just have the memory operations implemented. So if you get a memory read or write request, then this, handles that. So this is for memory reads, this is for memory writes. This generates the TLPs in response to that operation. And then down here, this is receiving that kind of multiplex configuration information. So depending on what the data is that's currently being presented, it will extract, the payload and read request sizes, bus num fields, and some MSI information as well. And then I have some tests here for testing a bunch of memory operations, testing a bunch of DMA operations, and then I guess this tests the MSI, but this is actually not quite set up completely, because this is code that I borrowed from the p-tile model that I was working on, and that one doesn't have a proper interface for MSI. For MSI, what you're doing is you're just issuing the individual write operations. So that's what this is doing here. It's doing tb.dma mem write. So That's one thing that I need to do, is actually properly implement the MSI interface on the H tile. So I think I'll go ahead and do that right now just to show how that works. All right. So Quartus is not happy about something. Cannot apply project assignments to the design due to illegal or conflicting assignments. Okay. What happened? Where is the actual error? Receiver channel data signal TXP0 is assigned to pin BH45, but the specified pin is not compatible with the data signal. Assign specified data signal to pin BL47. What? Hang on a second. Something weird is going on here. Where is my... Okay, where is the constraints file? Okay, so this is saying that TXP0, all right, so EPTXP0 is assigned to BL47, or wait a second. TXP0, there we go. TXP0 is assigned to BH45, yes, but the specified pin is not compatible with the data signal. Assign the specified data signal to BL47, and BL47 is what? BL47 is RXP. Wait, is there a crisscross that takes place somewhere? Hang on a second. This is why having the schematic is useful. Where is the PCIe edge connector? There it is. Okay, so we have PCIe RX1P. That goes to PCIe EP RX. Okay, that seems fine. All right, so that goes to page 22. All right, PCIe EP RX N11 goes to... Oh. All right, so the RX here is actually hooked up to TX on the FPGA. Interesting. Okay, well, that explains a few things. I guess what I need to do is go ahead and flip-flop the RX and TX over here. All right, so I'm going to go ahead and switch these around. Make that RX, that TX. And I go down here. All these RXs get switched. So all these become TX. And all of these become RX. All right. Let's see if it works this time. Okay. So yeah, this is why you do this stuff incrementally, right? You can catch these kind of weird schematic issues. I don't know why they have a crisscross in there. That doesn't make any sense. Usually you just run into that problem with things like UARTs. All right. Let's see if that works. That'll take a few minutes to build, if it works. Okay. So that is what the test bench looks like, and there's a couple other components that are necessary for the test bench. There's a make file, which is currently part of how cocotb runs everything. And then there's also a Verilog file, because the simulator needs some sort of Verilog code to run against. So this one defines all of the top-level ports, basically. So, and again, some of these are still set up for the P tile, so I just have them commented out. What I'm going to do right now, though, is get the interrupt interface working for the H tile. All right, so let me go ahead and locate the manual for this, and we will implement this properly. Okay, so what do we got? I don't know what the heck this is doing here. App error function number. That's not part of the interrupt interface. That should be, it's duplicated. All right, that's funny. Okay, so we've got the MSI request, MSI acknowledge, graphic class, MSI number, interrupt status. Wait, that's number of PFs -1 down to 0. All right, I'll have to take a look at what that signal is exactly. There's MSI function number. Yeah, okay. That's not too bad. All right, so we go to interrupt interface. This becomes app MSI request, MSI acknowledge, MSI TC, oops, TC, all right, and then MSI number, okay, all right, also MSI function number, and this is interrupt status, right? Yeah, okay. All right, so MSI request, that's just a 1 bit going in. MSI acknowledge is also 1 bit going out. Okay, MSI TC, that's 3 bits. MSI number, that's 5 bits. Function number is, I think that's just 2 bits. Function number, yeah, 2 bits. Yep. Okay, all that looks good. All right, and the one thing I'm not sure about is this other signal here, the int status pin. All right, let me see if this says anything about that. Int status htile. Okay, so legacy interrupts assertion of app int status causes an assertion. Okay, we need multiple PFs, bit 0 is for PF0, bit 1 is for PF1. Okay, not sure what the stories of that, but that's 4 bits. All right, or that's 4 bits. Okay. So these are the signals. So I'm going to go ahead and take all of these. That's also an input. Yes. All right. Oh, STS. Okay. Okay. Make sure I get all these correct. Okay. So that is the interface on the Verilog side. So now what I need to do is go to the htile model, and we're going to add the signals here. Well, we're actually not going to add them. We're going to replace the existing interrupt interface stuff here. So comes none. Okay, and this goes away. All right, and interrupt interface is then handled here. So same kind of thing. Oops. All right. Let's see here. Init signal. Okay, and let's see. What do we got then? Oh, we got to set the widths. And there's only one here. Okay. So MSI number. Oh, hang on a second. I'm missing one here. Yeah. It's request and acknowledge. All right. All right, I need to make sure I got the other end of that. PC, that should be 3. MSI num is 5. Function number is 2. Status is 4, and these go away. All right. Make sure I got the MSI request. I do. Request, acknowledge, PC num, func num, status. All right. Okay. So that's that. Now what I'm going to do is go over to test bench here, and I need to drive most of these guys to 0 except for acknowledge. All right, so this is all dot. Okay, set immediate value 0. All right, cool. So I'll just go ahead and replace all of that. All right, so those are the MSI connections. Right, so now for issuing MSI interrupts, what we can do is update the test here. So before I actually edit this, what I'm going to do is run the existing test bench real quick and make sure that that it works. All right, so we'll run it. Okay. So this is running all the tests. Definitely doing what it's supposed to do. Okay, cool. Now what I'm going to do is comment out the memory and DMA tests. So we only run the interrupt test. Okay, there we go. So what this does is it tests all 31 or all 32 MSI interrupts and makes sure that they're all handled correctly. So that's what it does. Send MSI 31 and then MSI interrupt. There we go. 1F, that's interrupt 31. So that worked. Okay. So what I need to do now is update this so it drives the MSI interrupt signals instead. All right, so the signals that we need are not the error interface. It's these guys. Okay. Okay, so instead of doing that, all right, so this is all going to be dot. Don't need ACK. All right, so this one we're going to set to 1. All right, TC, we're going to set that to 0. MSI number, we're going to set that to K. And the function number, we're going to set that to 0. We're just using the one function. All right, so what we do is we wait for the clock edge. And after this, what we're going to do is wait for the MSI acknowledgement signal to go high. By ACK. All right. And then at that point, we can set the request low. Actually, I'm going to do this differently. Instead of doing that, I'm going to put this in a loop. While not dot app by ACK value. Okay, so we'll do that, and then we'll wait for that, and then at the end we'll do that. Okay. All right, and then at that point, it should have issued the MSI. I mean, with the way it's currently set up, it won't, but we'll see what this does in terms of the test here. So yeah, okay, this fails. Oops. Unresolvable bit in binary string Z. I see. Okay, so I missed something in the model here in terms of what did I forget? Oh, I forgot to connect the signals. Yes, all right. Do is go over here and select all of these. Right, this needs to go here. I need to connect the signals here. Interrupt interface. Yes. All right. Dot. Okay, there we go. Okay, so those are connected to the model now. So this will run, and it's gonna hang. Perfect. Okay, because that acknowledgement signal never gets set high. Okay, so let's see. I think we finally got Quartus working now. It's now well into the fitter, so that's good. We'll check on that once that's done. Okay, so that is piece number 1. We have the test bench doing something. Now what I need to do is implement the other end, and this is going to be in the model. So I already have this run interrupt logic code here, kind of waiting. Now what I need to do, I guess I don't have this set up here. So this interrupt logic is after the FC logic. All right, so this is going to be if self.app MSI request. Okay, if we have the request signal connected, then we're going to do cocotbext-pcie self.run interrupt logic. Okay, Now for the interrupt logic, this is going to be relatively simple, actually. So for this, what we're going to do is, do I still have the signals line around here? Yeah, there we go. Okay. All right. So for the interrupt interface, all we need to do now is wait for that request signal to go high. Yeah, all right, so file not self.app.pcie request value here. All right, and then we're going to wait for a rising edge on the clock. All right, so once we see the request go high, now we need to issue the interrupt here. And then we're going to set the acknowledgement high. All right, and then we're going to wait for the request to fall. And then we're going to reset the acknowledgement signal. Oops. Set that back to 0. Okay. So let's see. That looks pretty good so far. I got the request and acknowledgement taken care of. All right, so let's see. Is this going to blow up in my face? I hope not. Okay, MSI request.value.integer. This error is coming from the code that I just wrote. Yes, all right. I thought I set that to 0. I may have missed that line. Let's see. Go back over here. MSI. Oh, maybe. Why would it be hitting that? Not sure. Well, I'm going to go ahead and put a startup delay here. Oh, actually, I need to put this in a while true. Yeah. Okay, so I'm going to wait 1 cycle before doing that. Let's see if this improves anything. Okay. All right, it still hangs. That's good, because I haven't actually issued the MSI yet. All right. All right, so now the question is, how are we going to do that? I'm going to pull a line of code from a different model. This is the UltraScale Plus model, which has the MSI stuff implemented down here. So if we have an MSI interrupt request, let's see here. This will then look at functions.msicap.issue MSI interrupt. Okay, there we go. That's what I need to do. 1 line of code. All right. So I will go down here to HTile model. We'll then issue the interrupt using this here. All right. So this is going to be let's see. When we see the request, then I can go ahead and use this here. This is self.msi or app MSI num value.integer. All right, then I'm going to go ahead and issue this based on self.app.msi. Oh, that's right. All right, but this one should be function number. Okay, cool. And then I don't have attr, but I do have tc. Be self.app.msi tc. Okay. All right, so let's see if that works. And something is complaining about my line being long. Whatever, I'll deal with that later. And there we go. MSI works because all of those MSIs were issued and handled appropriately. All right. Cool, and we can actually take a look. If I clean this here, I'll do make waves equals 1. We can take a look at what that looks like on the waveform viewer. Let's see, this is going to be test PCIe htile.fst. All right. And we can take a look at this. All right, where are, yeah, here are the MSIs being issued. So there we go, we set the request high, the acknowledgement goes high, and it goes lower, it goes low again once this falls. So yeah, that's pretty straightforward. Actually, is that correct? Let me take a look at the documentation for this here. MSI acknowledge, okay, it asserts for 1 clock cycle. Okay. So I'm actually going to reorder these things here. There we go. So I will go ahead and set it low and then wait for the acknowledgement to be, or wait for the request to be deasserted before moving on to the next thing. All right, so let's run this again and see what that looks like. All right, there you go. We have, so that gets asserted. This is then high for 1 clock cycle, and then they're released. Okay, perfect. Okay, not bad. So that works. All right. So the next thing that I need to do now is take a look at actually getting this this shim working. And this is going to be the more complicated part of this whole operation, because what we need to do is take the PCIe IP core interface on the Intel IP core and adapt it to the generic interface that the DMA engines use. All right, so let's see here. I think this is going to be working well enough. If something wonky is going on, I can come back and take a look at the model later. All right, so let's put that one aside. Okay. Let's see here. So what I need to do for this model, do I have a test bench for it? I don't think I do. I have a test bench for the ultra-scale model, but I don't have one for the H-tile model yet. So I'm going to go ahead and make a copy of that. Okay. Cool. All right, so this is PCIe H-tile IF. Okay, so we'll go ahead and clean that out of there. All right, so we go into H-tile IF. We go ahead and rename this. So this is going to be the H-tile IF. All right. IF, that's fine. Make file. All right, so this is going to be looking at the H-tile IF here. All right, and then I have the RX and TX here. All right, and remove those for now. All right, and I need to go ahead and update all of the parameters here because these are for the ultra-scale devices. All right, let's see here. So there's the make file for H-tile, and let's see, I have, well, I don't need that one, but I do need this one. All right. Okay, so what I'm testing here is now going to be H-tile shim code, which is this module. So I need to go ahead and make sure all of these parameters are reflected properly in the makefile. Let's see here. So I'm just going to make a copy of this so I have a nice reference. Okay, so MSI count, MSI enable, I got that. F count, that's here. Read max, read request size. Hang on a second. Are these actually even related to this? Oh, they are, okay. Read max payload size field. Read max. I'm drawing a blank on what these correspond to. Read X tag enable. Oh, these are okay. So for the ultra-scale devices, you have to jump through a couple of hoops to read some of these settings. That's right. So those are not present here because those just come out of the core directly out of that configuration interface. Okay, so F count, BF count, PF count, sequence number width. TX sequence number width, I'm just going to set that to 6. Okay, TX sequence number count, that's going to be seg count. Well, I may need to do something different. Well, okay, this is going to be ram seg count. Okay. Oh. Let's see. It looks like Quartus is done with generating the configuration for the Stratix 10 MX FPGA. So this doesn't have the PCI Express user logic in it. It's just the bare IP core, but that should be enough to actually test and see if it enumerates. So I'm going to go ahead and whack this card in, and we'll see if it enumerates. All right, so timing analyzer. Did this report any issues? No failing endpoints. All right, cool. Hold on a second. Let me get this card plugged in. All right, there we go. The dev board is now installed in my development machine, so let's go ahead and load this over JTAG. And standard issue Intel software taking a long time to do things. All right, let me see. Oh, it picked up the dev kit. That's good. Let me run auto detect. Dumpty dumpty dump. Okay. Yeah, I think that's right. Okay, that looks right. And I guess that management FPGA is also on there. Yeah, all right. Okay, cool. So I will go ahead and program this guy. All right, I need to change file. That board is loud. I think it's probably coming through on the mic here. Apologies for that. I'll turn that off once this test is done. All right, so program that and I hit start. Okay, there we go. All right. So I'm going to go ahead and log into that computer now. It might not be finished booting yet. These servers take a couple minutes to boot. They have the Supermicro AMD EPIC motherboards. So they take a couple minutes in post to do stuff, and they gotta wait for the IPMI subsystem to do its thing. Okay, there we go. Well, I'll just do LSPCI. Okay, that's a different board I have in there. I gotta reboot for it to re-enumerate. All right, we'll give that a minute. Once it reboots, then we'll see if that card enumerated. So yeah, I think that is, what was that one? Oh yeah, that's the Silicom card. That's right. Yeah. That's Kintex Ultrascale part. All right, now let's go ahead and get rid of this stuff for now. We'll give that a minute to finish rebooting. All right, so where were we here? Going through these, I got MSI count, MSI enable, F count, BF count, PF count, TX sequence number width. Okay, let's see. TLP segment header width. All right, that looks fine. Okay, so this is going to be RAM seg count. Times could be param seg data width. Well, no TLP. All right. Okay, and that's over TLP seg count. Okay, TLP seg count is 1. All right, and then I need 3 of these here. I need the segment count. That's 1, and then the seg data width be 256. All right, and then the seg empty width. Let's see. So this is seg data width over. Oh, I need to C-log 2 of that. All right. I'll deal with that later. So let's see. 256 over 32 is 8. So that means the width of these is 3. I will get that properly parameterized a bit later. All right, so that's all the parameters here. Param seg count, so I can get rid of that. All right. Okay, now I need to go ahead and update these. Let's see, so most of these are, oh, this is not RQ sequence number width. This just goes away. Yeah, all right, there we go. So I have these 3. And some of the other ones need to be removed. All right, cool. That goes there, and this goes here. Those get removed. All right, TX sequence number, yeah, those are fine. VF count, VF count, those go away. All right, cool. And then again, same thing, that, and I do that. Okay, so I remove these. That one goes away. All right, and I have those, those go away. All right. Okay, some progress. All right, so that looks better. Okay, now let's see. What do I need to do next? Let me see if this thing is rebooted. Did it reboot? Yes, it did. Hey, all right, we have another device. So that is going to be the Stratix 10 MX FPGA there. Now, somebody said no noise from the card. I can hear kind of a high-pitched thing on the microphone occasionally. So it's not much, but I don't know. I guess maybe that means my ears have not deteriorated as much as I thought they might have. All right. Okay, so unassigned class. Yeah, so that is going to be... Actually, I don't think I changed the class code, so I'm not sure what that was set to. All right, anyway, let's take a look at what LSPCI says for that card in detail. All right. So let's see, we got 2 bars, right? I set up 2 16 megabyte bars, so that's what we see there, region 0, region 2. let's see, PCI power management. Okay, MSI, we got 32 channels available, but only one enabled because it hasn't been initialized by the driver or anything. Capabilities, PCI Express. All right, so we got link capacity, port number 1, speed 8 gigatransfers per second, which is Gen 3 width by 8. Okay, status 8 by 8. Looks good. The link came up properly. And there's also AER, virtual channel, secondary PCI Express, and then vendor specific. So I think this one down here, 1172, I think is Altera's PCIe vendor ID. I think this has to do with the CVP, right? The configuration by protocol. That's done through something sitting in the configuration space, and I think that's what this is. I believe. Yeah. Yeah. So that enumerated. All right. Cool. So I'll go ahead and power that off for now. And next time we turn that on, hopefully we'll actually have something sitting behind the PCI Express IP core. All right. Much quieter now. Okay. So where were we here? Okay, this is in terms of simulating the H-tile interface here. So here are the files for the H-tile and the test bench. Okay, so let's see. So what I'm going to go ahead and do is run this, and let's see how many errors we get. Unexpected argument makefile. All right, where did that come from then? TLP seg data width. Parameter TLP seg count. VF count, VF count. Expected argument makefile, unexpected argument 32. Oh, that's the problem. Okay, yeah, everything failed. That's fine. Okay, because this is still looking for ultra scale stuff, but it at least tried to build it, and we didn't get any errors from Icarus Verilog. Right. Okay, so let's take a look now at this guy. What we're going to do is switch this over to import the p-tile. Let me take a look. Actually, did I expose all of this properly here? Yeah, so this should be Intel H-tile. Yeah, that should be fine. And then I want to import H-tile PCIe device, right? Okay, and I'm not using the AXI stream bus. I actually need to import these as well from here. Okay, there we go. I have that. All right. Okay, so now what I need to do is plug in. I think I can just copy a lot of this from the test bench that I was using previously for the H-tile model. Right, here's H-tile model test bench, so I can go ahead and copy, well, maybe not all of this, but well, we'll start with that. Lots and lots and lots of signals. Okay. Okay, so this is host side H-tile PCIe device. All right, Gen 3. Okay, the rest of this will be muted based on other settings. We have all of these connections. RX interface, TX interface, RX flow control, TX flow control, interrupt interface. So what I'm going to do is actually comment out most of this stuff because it's not going to be present in the interface module that I'm going to be testing here. Okay. In fact, I don't think this one's present either, so comment everything out to begin with, and then I'll start bringing stuff back. All right, so what do we have here so far? Well, I'm actually going to delete the ultra scale code here. Okay, All right, so this block here is the host side of the shim. This is the device side of the shim. So basically for this, I took most of the stuff that's sitting more or less in the test bench code here, all of this stuff, and I encapsulate it in a module so I can pull that in just for testing this this shim code. That makes things a lot easier to integrate. All right, so this goes ahead and connects it to the root complex. This sets up the various bars, and let's see. And I think we're pretty much good to go here. Well, all right, so that's fine. I'm going to remove everything that's related to the ultrascale IP for the time being. Okay, so this .rst, oh, that was connected to the user reset. Yeah, okay, so that should be fine. I just realized that I think all of the reset signals coming out of this are all inverted. So I'm going to have to drive the reset line from the test bench, which is, you know, not that big of a deal. All right, so what I'm going to do here is that .rst, set that to 1. So it starts out held in reset, and then I'm going to go ahead and connect the core clock out. This is going to be going to .clock. Yeah, I guess the other thing is I don't have a lot of these pins present. So I may need to make a couple of modifications to the model so it doesn't crash if not all these pins are there. All right. That also means the reset status connections are not there. Maybe that's not a problem. Let me take a look at how the reset is implemented here. At this point, I'm going for quick and dirty. See if we can get it up and running. I can clean up some of these odds and ends a little bit later. Okay, so I think if most of these are none, that's not going to be an issue. Yeah, I need to clean that up a little bit, but you know, all right. I think that will work. Okay, so what I'm going to do is I'll wait 100 nanoseconds after the start, and then I will do see .rst. I will set that to 0. I will probably circle back at some point and clean that up. So comment that out. Same kind of thing here. That out, okay. Okay, cool. And the other thing I'm going to do is I'm only going to test this with no back pressure for now, because there are a few things that need to be implemented in terms of properly dealing with the back pressure for the Avalon streaming interfaces, because they are a little bit different. I'm also only going to run the memory tests for now. So we'll start with that, and then once those work, then we can take a look at the DMA tests. All right. Let's see here. Well, the other thing I need to comment out for now is all the I/O related stuff, because I need to do some additional work for that to be correctly handled. All right. Because of the fact that it reports an oddball bar ID. Okay, let me see what happens now if I run this. No object RX-par error. All right, I don't have those connected. So I will comment those out. All right. All right, something is not happy here. What signal? It's TL config func. Okay, so I think I have that set incorrectly here. So I'll go over here, TL config func. Yeah, that should be 1, and this should be 31. All right. And these I don't think are used anywhere else at the moment. All right. Run that then. What do we get? Okay. All right, so this gets all the way down to it tried to perform an operation and it timed out. As expected, because we have nothing to bridge the gap at the moment. All right. Test bench is now trying to run, so now we can actually start writing some HDL perhaps. Okay. K-wave, this is now PCIe if.fst. All right. Take a look at this. I have a lot of stuff that's not connected yet. All right, that's fine. Bus number, clock X tag enable, yeah. All right, so the first thing that I can do that's pretty straightforward is to go into, let's see here. I can go ahead and pull in this PCIe htile config block. And this one, this one is kind of a pain in the butt because it's basically kind of a direct translation from what's in the user manual. But what this does is it picks apart these time domain multiplexed signals. I'm going to go ahead and whack that in here. And with this module, what we can do is extract a couple of these signals, like the X tag enable, the bus number, and the max read request and payload size signals. Those all come out of here. All right, so we got PF count, pass that through. PF count, yep, a dot here. Okay. PCIe htile config inst. Okay, and then I have clock and reset. Oops, clock and reset. There we go. Configuration input. All right. Can I match the name here? No, I guess not. All right. I don't need these. I don't really like putting underscores like that on the end of signals, so I'm going to go ahead and edit these to remove those. Okay, one more. Function. Okay, there we go. Perfect. All right, so that is that, and now I have all of the outputs here. Okay. Well, all right, so let's see. I have X tag enable, max read request size, max read request size, max payload size, max payload size. And there was also bus number, there we go. All right. Now let's see if that extracts that appropriately. Where's my make file? Let's make sure we got that in the make file. Yeah, okay. Also put this htile MSI. All right. Let's run that. Oops. I'm gonna run that over here and AR core error mask. I forgot to define something. Okay. Would not surprise me if I have some silly mistakes in here. First time I've tried running this code. Okay, so that's line 172. Error core mask. AER. Oh, CORR. Well. Okay, so that ran. No crashes. Let's take a look at this now. Okay, here we go. Look, we can see xtag enable. That pops up after a while. Because that's what happens is that will be set during the PCI Express enumeration process. And then these are being driven out of the core periodically. We can see kind of the TDM here, the address, right? Cycling through, I think it goes between 0 and 9. So when the correct one comes up, then it will pull these signals out. So we can see the bus number is set to 1, the max read request size is set to 2, which corresponds to 512 bytes, and the xtag enable turns on. So we're starting to see a few signs of life here. Okay, let's see, what's next then? What's next is to start working on actually handling the TLPs. Right, so at this point, we have a TLP that's coming out of the test bench. So we can see we have a startup packet, we have valid, we have end of packet, so it's a one cycle transfer. We see st empty of 4, right? So that means st empty of 4. What does that mean here? That means there's 4 empty lanes here. So that means this packet is 4 bytes long. So yeah, the length of this transfer is going to be 8 minus this number, because it's 256-bit wide bus that's transferring 8 32-bit D words at a time. So this is 4, and that means this is 4 D words in size. Okay, that's pretty straightforward. So what we need to do is take this and convert it to, let's see, we need to do 2 things, right? We need to look at the TLP header to figure out, is it a request or a completion? So this is going to be a write request, I think. And the write requests, what we're going to do is turn them around and send them out of the appropriate interface, which is going to be the RX request TLP here. So yeah. And for this, it's going to be relatively similar to what you do for the Xilinx devices here with the CQ module, because this is going to be accepting a completion or a completer request over a streaming interface, which has a header attached to it. What we're going to have to do is the same kind of thing. We'll have to peel off the header. I don't know if we need to make any other changes, but we need to peel off the header and stick that in the sideband data and pass the rest of it through. The other thing that we need to do is, since we need to figure out whether we're looking at a a request packet or a completion packet on the RX path, is we kind of need to bifurcate this in 2 directions, and we're going to have 2 outputs and basically an internal FIFO for that. So this one doesn't have the internal FIFO, and this one has to do a lot more work to kind of reorganize the TLP header. One of the advantages of the Intel FPGAs is that they use basically standard TLP. They use standard TLPs. They don't do something wonky like with Xilinx, where they have a different TLP format. All right, so let's see here. Yeah, they have their own request type field that you have to remap stuff into. So for the Intel one, it's a little bit simpler because you don't need to do that. All right, so what I'm going to start with doing here is I'm going to copy not all of this, but a large portion of this into RX code here, so we can start massaging it basically into something that's going to be more useful. Let's see, in terms of all of the checks that are done here, was there anything else that I need here? So this is all, yeah, that's all fine. All right, so these are good. All right, so this is for the RX request TLP. And we also need stuff for the RX completion. But if we're putting in FIFOs, it might make sense to reorganize things a little bit. So the FIFOs, well, let's see. Before I do the FIFOs, I'm going to look at the RX completion stuff here. I can copy these and go ahead and pop these in here. So we have the request and we have the completion that's going out. All right. Let me see if it complains about anything with that. It shouldn't. Okay. So there we go. These now have signal levels defined. All right. So when the data comes in, we need to handle that on the input side. So let's see here. Input state. I'm not sure how many states we're going to need. I think just 2. And the other thing I'm going to have to do at some point is come back and make this work for a segmented interface, which is what you need for the 64-bit connections. Or not 64-bit, that for when you're running PCIe Gen 3x16, then you need to run in 2 segments. And it's also the same deal with the Stratix 10 DX. If you're doing anything x16, it's segmented. All right, so I'm going to go ahead and get this state register working here. And I'm also going to go ahead and well, let's see here. Let's get the input parsing working first before output works. All right, so this block here is storing the previous transfer cycle because we need to look at we're peeling off the header. We need to be able to produce, full data transfers, and that means we need to be looking at 2 cycles worth of data. So we have to store the previous cycle for a bit before we can parse it. So I need to go ahead and create a couple of registers to store this for the packets coming from the Intel IP core. We're basically storing everything. All right, so that's all going to be reg. All right, and then I don't have a ready. These are all going to be for the internal storage here. Okay. And I need next for all these as well. Do I have a valid? Yes, there is a valid. All right, cool. All right, settle these to 0. And then next. All right, cool. So I have data empty, SOP, EOP, valid, VF active, function number, VF number, bar range. Okay. EQ to user. All right, so that basically replaces all of these. Okay, so I take that. And I also need to put together another one of these here. This is now wire. I guess I don't have a single variable right now, or a single parameter for the full width. So I'll just do seg count times seg data width times 2 minus 1 down to 0 of rx_st data. I'll make that full, and then this will be a combination of these two. So this is going to be rx_st data and rx_st data int reg. All right, cool. Same idea there. All right, so now we go down to the bottom and I need to store all of these. Okay, and this is, oh, these are also wrong. Let's see here. So this is RxST valid. And RxST ready. All right, cool. And down here, I need to go ahead and put all these registers in again. All right, there we go. And this one needs to be reset to 0. CPL, all right. Okay, let's see. So for the ready one, I need to take a look at how flow control works in the receive direction really quick on these devices. All right, so if we look at the RX interface here, ready input, well, that doesn't say anything about any delays. On some of these, there's a huge delay between the ready and the response to the ready. Yeah, okay. Timing diagram illustrates the timing of the RX interface. Yeah, okay. The RxST valid signal deasserts within 17 cycles of the RxST ready deassertion for variants other than the Gen 3x16 variant, and within 18 cycles for the Gen 3x16 variant. Okay, so yeah, you drop ready low, and then you got to be able to hold quite a few cycles before you can actually do much about that, right? So yeah, you have to deassert the ready signal like 17 or 18 cycles early. So what I'm going to do in this case is I'm going to implement a couple of output FIFOs that are 32 entries deep, and if the output FIFOs fall below you know, half, then that will result in the input, you know, deasserting the ready. I may actually need to adjust that, right? Because half of 32 is 16, and we're talking about 17 or 18. So maybe if we get more than like 8 entries in the FIFO, then we have to back off. Right. Okay. So in that case, the ready signal, I'm going to start right now just by signing it high. And then once I get the FIFOs implemented, then we can change that. Okay, so I get rid of that. All right. And this one also, I get to ignore the ready because we can't do that on a cycle-by-cycle basis. The handshaking is slightly different between AXI Stream and Avalon, because with AXI Stream, you look at both the ready and the valid, right? Data is only transferred when both ready and valid are high. But for Avalon, it works differently. You just don't set the valid in the first place if the ready signal is low. If the valid signal is high, then the transfer is taking place even if the ready signal is low. So this is something I need to update in a couple of places in order to properly handle back pressure. So yeah, for the time being, back pressure is not going to work because the models don't. The models that I have right now, I think, are still using more the AXI Stream kind of variety, which, you know, it works fine for the ultra scale devices, but it's not appropriate here for the Intel devices. Okay, so let's see what happened now. It accepted the packet, right? Oh, and I'm not seeing the new stuff here because I need to look in the RX direction here. Okay. Oh, and then I guess I also need to preload a bunch of these too. So, oh, these are all, oops. All right, that's not what I wanted actually. That goes here. Okay, and then these are going to be drawing from the input, like so. All right, try that. All right, there we go. That now accepts the input, and that is stored internally here. So we can see the tvalid int reg goes high, and that stores the data. And in the st data full, we basically have 2 copies of the TLP here. And the idea is that we're going to work on one of them. Let's see, which is the right one that we're going to work on? Probably this one. How did that build that up there? Started out, yeah. So the packet comes in up here, and then it gets shifted down. 0201. That's a different. Why does it have a different encoding there? Well, let's see, the RxST data. Oh, yeah, so the data changed to different encoding there, coming from the model. Yeah, and then valid was high for 2 cycles. So that's actually, it's generating two packets. Let's take a look at what's going on here in the test bench, just so we're all on the same page, right? So what does the test do? It does memory operation, 32-bit bar, length 0, offset 0. So it's trying to do a length 0 write, right? Let me take a look at the test bench for that. What is it doing here? Test PCIe tile or H-tile IF. All right, so what this is going to do here, it's going to do memwrite, and then it's going to do memread. And then it's going to do another memread. Hang on a second. Right, so this first memread here, this one is just for delay purposes. So we know that the write has taken place because that read operation, or the write operation, cannot pass the read operation. So once we get the completion back from the read, then we know that the write has taken place. I may actually need to modify that temporarily so we can check to make sure the write path is working. All right, so what do we have going on here? Right, so it issues there's a bunch of DLLP stuff, but we issue a TLP for the memwrite operation. So we see here memwrite, and where is the address? There's the address, right? And there should be also a length here, right? First BE, last BE are all zeros, and the length should be 1. Yeah, length 1. So this is, so it's doing a 0 length write, so it shouldn't actually affect the target, data, but that's what the TLP looks like. Okay, so that goes through. Let's see, this gets handed off to, where is this? This is an X receive in the port. That gets handed off to the H-tile model, and then this goes to the interface. That is the actual TLP payload data that gets sent, right? First D word, second, third, fourth, right? And you can see that's the address, all right. And then, or actually, so that's the address, and then that's the data, right? The parity bits and whatnot. So that gets driven into the design, and then it generates another TLP. This one is the read request, and that one also gets driven into the design. So there's the other one. So yeah, we can see here's our 4, here's our 2. So that should correspond to, yeah, right. So this one has this one has a 2 in it now, but before it accepted that second TLP, there's the 4, and then the second TLP, this has that 2 in there. All right, cool. So that's working correctly. We are seeing, well, we're seeing the first TLP and then the second TLP. That's kind of a little bit of an implementation detail here. This is mainly important so that if we have a TLP that's more than what is this, 32 bytes, then we can see a contiguous payload that's at least 32 bytes. All right, let's go back to what I was working on before here in terms of the RX path. All right, so when this thing shows up, what do we need to do here? All right, so if we have the valid, let's see, this is the internal register here. This is rxst valid int reg. Okay, and I'm going to set that one aside for now because we're not feeding things back that way. Okay. And then down here is for the payload and the same kind of thing. Okay. Is that the int? Yes. Okay, that's right. Okay. And I can go ahead and put that in like that. All right. So let's see. This is looking at the type field, right? The length, or no, not the length and type. This is looking at the Xilinx proprietary field. We don't need to do that here. We just need to pass this through as is. The main thing that we need to sort out is what we're doing with the payload, because there's two possible offsets for the payload depending on the length of the header. So let me think about this for a minute here. Wait, what sizes are allowed here? I think we're only going to be doing either 256 or 512 bits. So that actually removes a lot of these conditionals. So the Xilinx ones, if it's 64 bits wide, you're not going to get the whole header in one shot, and that complicates things a little bit. So in this case, what are all the allowed sizes? Let me take another real quick look at the IP core configuration. Let's see, files. I think it only supports 256 bits and 512 bits, but let's confirm that. It takes a minute to load. Anyway, I'm pretty sure it doesn't support 64, so that means all of this down at the bottom can go away, and this can go away here. Okay. Maybe it'll be faster just to look at the manual. Yeah, so they only describe a 256-bit interface and a 512-bit interface. Yeah, so that means everything either 128 or 256 is not going to be a consideration here. And I can probably also add another little bit of information here, like the segment width has to be 256. Seg data width has to be 256, yeah. So that must be 256. Okay, cool. Yeah, and eventually I need to support with seg count equal 2, but you know, one step at a time, right? Yeah, okay, and that also removes this if block as well. Okay. At this point, yeah, things are starting to fall into place a little bit here. Okay, so I don't need to do any of this stuff here. I'm going to go ahead and get rid of that, because all of this code is just in terms of reformatting the TLP header from the ultrascale specific one to the standard PCIe TLP format. So what I'm going to do here is basically just peel off the header. I think I can do that. I don't need to do anything special here. This is just going to be coming directly from the CQT data. Or not CQT data, right? This is coming from the full, this one. All right, this is then 127 to 0. Actually, that might not be right. I think I need to potentially reverse these. Yeah, do we need to byte reverse this or just D-word reverse it? Let me take a look at, I think here. Let me take a look at the PCIe specification real quick. All right, so let's see. Where is the transaction layer specification? Okay. All right, so this is what it looks like in byte 0. We have the format and type. Okay, and then after that, all right, so let's track where that field is ending up. In the HTile interface code, where do we put the format and type? Let's see, HTile interface. All right, so this is, all right, so, okay, so we're packing the header and the data in different endianness. That makes sense? Let's see here. So the header, what did that one look like here? So we have 02. All right, so the field that we saw change between 04 and 02. 1, 2, 3, 4, 5, 6, 7, 8. Right, so that 4 became 2, and that's I think the type field, right? So I think I need to D-word reverse this, which is actually not too bad. So what I'm going to do here is I'm going to set 127 to 96, I think. Oops, I didn't want to put that in. Okay. This is going to be 31 to 0. This is 32, 63, and then 64 to 95, then 96 to 127. All right, and then I got to reverse all these here. This is going to be 0 to 31. And let's see, 32 to 63, and 4 to 96. All right. Let me see if that looks right in terms of what's coming out of the header. Actually, I may need to add a couple of additional lines here. Okay. We put these in and put these in as well. All right. Okay, there we go. There. All right. So this starts out for all right, so this is correct, but this one doesn't look right. Oh, I think that's because it changed states, right? Maybe. Oh, it shouldn't have changed states. Why did this get shifted? Yeah, so that does look correct for the first one. But for the second one, oh, maybe that's fine, actually. I thought the 4 and the 2 ended up in the same spot. I don't think they did. Yeah, okay, so for the read request, so that would have been read request with a 32, sorry, with a 3D word header, I think, and no data. So what would the type be for that? If that encodes a 0, then I think we're okay. 3D word header, no data, does encode a 0. Okay, that makes sense. And 3D word header with data is a 1. All right, so I think that looks okay. All right, so this header I think is correct now. So now the next thing that we need to do is figure out whether or not this is a completion packet or a request packet. Let's see, so that's the header. So that takes care of all of this. All right. And now I also need to pass through the bar ID and the function number. So this becomes rxst bar range. And rxst function number. Okay, those get passed through. Let's see, rx request TLP data next. Okay, and let's see, yeah, so this is then looking at, oops, that's not going to be PCIe data width, this is going to be what I have up here. It's also not CQT data, right? This is the full, yeah, okay. All right, making some progress here. Input frame next. This one is indicating whether or not we are inside of a frame. That's rather important. All right, so I'll go ahead and uncomment this. All right, so tlast int. So this is going to be actually the rx request TLP, no, rxst eop int. Okay, rxst TLP valid next, set that high, eop I set next. Okay, that looks good. CQT valid int. And this is rxst valid int next. So I clear that out. TLP input frame 0 and then go to idle. All right. Okay, and then one here is okay, this is rxst valid. Okay. Rx, okay, so that one moves over to payload. All right. Otherwise, I stay in idle. Okay. Okay, so again, this is the same kind of thing. I'm looking at the end of frame rx steop int reg. All right, so basically what I'm doing here is I'm checking to see if I have the end of was it 95 to 64. Yep, that would have been a bug. Okay. All right, so where was I here? So what I'm doing in this case is I'm looking at the end of the frame here. So I know I have a frame. Yeah, I'm in idle. So I know I'm not in the middle of a frame. I got to be at the beginning of a frame as soon as I see something. So if I have a frame, then I can go ahead and extract the header from it, and I can extract the payload data. And this is actually not completely correct at the moment, because I'm going to need to extract from one of two possible offsets depending on the length and type field. So I'm going to need to add another variable for that. Right. Anyway, so this goes ahead and extracts that and puts it in the data. It marks that we have a starter packet, and it says that we don't have an end of packet yet. It says we're in a frame. I'm not sure if I use, where else do I use this TLP frame? Maybe this is not used. Oh, maybe this was used for the 64-bit stuff. Let me see here. I think that was the case. So this is going to be CQ, and the TLP input frame. Yeah, so that was used for when we have a narrower input here, when we get the entire header in the first cycle. Okay, so I actually don't need this, or when we don't get any payload in the first cycle, rather. Okay, so I don't actually need that. That one will go away. That. All right. Okay, so now what we're doing here is we're looking to see, did we get the end of the packet in the current cycle? If we did, then we go ahead and transfer it out. We mark that we've already dealt with that current piece of the packet, and then we stay in idle. Alternatively, if we've accepted this cycle and there's another cycle that's waiting, then we have the payload from that cycle, so we'll go ahead and output that and move into the payload section down here. Otherwise, we stay in idle. Yeah, we stay in idle until we see this valid as well, and then we shift that out. Right, okay, and then in the payload section, we're basically doing the same thing. We're looking for the end of the frame. If we see the end of the frame, then we shift it out. Let's see, CQT, oops, I need to change this one to this one. And then we go back to idle. And this one, again, the same thing. If we have the other half, then we go ahead and output it. And then we stay here. Otherwise, we stay here. Simple. Okay. All right. So now the question is, if I run this, what happens? Whoa. That did some more stuff. I think, anyway. I see a bunch of memory reads. All right, something generated a bunch of spurious reads. Yeah, okay, so here is the write request. All right, so let's see if the write request went through here. So yeah, I see memory write. This is coming from the PCIe interface model here. That's modeling the generic PCIe interface. It got a memory write, and I guess I didn't print out any parameters beyond just that it was some sort of a write. Oh, but we do have the TLP here, right? Here's the TLP, byte array all zeros, mem write, DC0, length 1. Let's see, first BE, last BE0, address. That address looks correct. Okay, so we got a TLP for a memory write, so it carried out the write. Okay, but now this then generated a bunch of TLP ready. Let's see, so what happened here then? Nothing reset this signal. Why did that happen? So this is RX request TLP ready, or something keeps setting it. All right, the state TLP input state reg. Oh, unless the, all right, so input here, RxST valid. Yeah, so that's only valid for 2 cycles. Oh, but the int reg, all right.
That one is still high. What is going on here then? That gets set to 0, and then we go back to idle. Yeah, so in both of them we were getting EOP, and then, so this should have been, oh wait, VF active. Oops. RxST valid int next. Okay. That's what I wanted to do. Okay. Okay. Let's see if that was better behaved. Ah, there we go. Excellent. So there we go. We have Rx request TLP valid. We've transferred through 2 TLPs. Perfect. Okay. Now, at this point, I don't have the other direction working. So what I'm going to do now is I'm going to go over to the test bench that I have here, the htile test bench, and I'm going to remove this memory read and replace it. Well, let me think here. Well, the next thing we do is just the proper memory read to check for the test data. All right, I'm going to leave that one for the time being. We'll see if we can make this work. Well, I got to implement the FIFO, I think. Yeah, I need to implement 2 FIFOs here. One for each of the completion packets and for the request packets that are coming in. So let's go ahead and implement the FIFOs, and then we'll continue from there. All right, so I can get rid of these combinatorial inputs real quick here. Oops. All right, that goes away, and this also goes away there. Yep, okay. And this goes away as well. All right. Now the question is, do I have something that I can draw that from? A nice little FIFO, this little output FIFO module. Let me take a look. Do I have, let's see, the AXI master right, maybe? Yeah, this has an output FIFO. All right, so I will steal this output FIFO and we will use that. All right, so RX, so I need 2 of these output FIFOs here. Well, I'm gonna edit this one first and get all the signal names updated, and then we'll go from there. The difference between these 2 is the requests have the bar ID and function number, and everything else does not. All right, so I'll go ahead. Oh, there's one other thing I need actually from, I pulled this from, yeah, from AXI master, right? There's also internal data path here for writing stuff into the FIFO. All right, so I'm going to go ahead and whack this down over here somewhere. Okay. All right, cool. So I'm going to go ahead then. I'm going to take the request to bar, and that's going to go ahead and need to update this. So the ready signal, that's fine. All right. And all these are going to be regs because I need to set those. All right. All right, int, and one more time here, int. Okay. Is that what I need? I think that's what I need, right? So Rx request TLP data int. Yeah, all right, cool. And then I'm going to duplicate this for the completions, and those are going to lose a couple of signals here. So these requests are going to get replaced for that. And then what I'm going to do is get rid of the bar ID and function number. All right, perfect. That goes away. That is going to feed into the FIFOs. All right, so here's one of the FIFOs. And paste that here. All right, so I don't have the ready signal here, but I have the rest of these. Okay. And as part of this, I also need to comment out all of that and all of that and all of that. Okay. Okay, so this is the request TLP. Okay, so this is MAXIW data. All right, so these are fine. All right, so out FIFO read and write pointers. Okay, so I also need to add this as a parameter. I'm going to add it up here for now. Make it 5 for 32 entries. All right. Out FIFO full, out FIFO empty. Those are based off of those guys here. All right. Okay, and then I have out W data. All right, so now I'm going to go ahead and make another copy of these guys. And these all get this. This is 2 times out FIFO address with 1 down to 0. All right. And I'm going to add every single one of these registers here. Oops. That's all going to be distributed RAM. Okay. What I can actually do here is copy this. All right, so that will replace these guys. Okay, and then this is the ready signal here. Yeah, RX request ready int. All right, there we go. That comes off of that. All right. All right, and now I need to update all of this stuff. So these are going to be based off of the valid output here. Wait, I bet I do I want int on these? I don't want int on these. Okay. Oh, and I don't want regs on these either. These are the memory. All right. So now I take this RxTLP valid here, and I'm going to go ahead and do that. Okay. Okay, that becomes ready. That becomes valid int. That looks fine. That's half full reg. All right, and I can change that threshold. Okay, and then this one here is ready. Okay, and now I need to update all of these. So this is everything except valid that goes into these guys here. So valid, that goes away, and then go ahead and take this. All right, so these are all going to be int. Okay. Let's see. I'll go back to the beginning, duplicate that, paste that. Okay, there we go. And this is out FIFO. Okay, that looks good. So this is writing into the FIFO. And then I need to do this one more time for reading stuff out of the FIFO. All right, cool. Paste that in. Okay. I do want that. That's correct. Okay. Okay, and then I need to go ahead and paste this in right at the end of all of these guys. Oh. All right, there we go. And no valid there. Okay. Okay. So that should be driving the outputs now. So what I'm going to do here is instead of driving next for all of these are all going to drive int. Same with all these here, int. Well, yeah, that should be fine. All right, valid next here, and EOP. Oh, that's fine. Okay. All right, that's valid int. Yes. Okay, and then again. Okay, so by using the int ones, these are going into the FIFO. All right. So I think that will probably work. Not 100% sure, but let's try it. Oops. Where is that? Line 302. Ah, yeah, okay. I don't want those. Yeah, all right. Okay, so I will refresh this. The CPL ones went away. But it looks like the data, well, all right. So something didn't quite work, but that is some progress. All right, so yeah, the FIFO is just continuously being written. Oh, I know what happened. I forgot to specify what the default values of all of these things are. Yeah, okay, that, let's see here. Where was the data path? Internal data path. I need all of these. Yes, all right. Okay, so in this case, I can go ahead and start getting some of these set up here. So the header ones, this is actually just going to follow these always. I can probably do the same thing here. Bar ID and function number, I can follow those. Valid is 0, stop and EOP. And ready is not something I can assign. All right. All right, so let's try that again. There we go. That's better. So yeah, we can see now RX, so the TLP valid int, I write two things into the FIFO, and here we go, here's two things coming out of the FIFO. All right, that's perfect, and we can see the FIFO pointers change twice, so that's perfect. All right, so now this is for the requests, so I need to now duplicate the entire FIFO setup that I have here. All these output FIFOs, I need to duplicate this. So this is output FIFO for the requests. Call that the output request FIFO. And then I need to duplicate this. And this is going to be for the completion TLPs here. Okay, there we go. So there's the request, and this is for the completion. All right, and then I got to do, I need to remove now bar ID and function number from all of these. Bar ID and function number goes away. All right, that goes away here. Bar ID function number. Here we go again, bar ID, function number, bar ID, function number. Okay, cool. Let's see what that looks like. All right, no errors. That's a good start. All right, there's an error field, RX CPL TLP error. That only associated with the completions? I guess so. Where was that one? Output completion. Yeah, there. Okay, there it is. There's the error. All right, so I didn't actually want to remove both of those then, in that case. What I'm going to do is remove the function number, and then I'm going to replace the bar ID with the error. Just ERR. And it's forward error, and then the width of this is 4. All right, and I got to do it there, and I got to do it over here too. 4, all right, and then here. All right, that looks good. And then what I can do is I think I remove that here. So this then becomes error. Yes, and this is times 4. Okay. And then I can duplicate this stuff. Let's see here. So going to be for completions, completion, and then the TLP error. Actually, I don't need to bother with that error field. Now that I'm thinking about it, that's like an ultrascale specific thing. Yeah. Okay. So I'm going to remove that, and then that port just gets tied off. Yeah, the ultrascale devices like reporting errors with the completions, which, you know, simplifies some things a little bit. But that's a non-standard thing to do, so. All right, so I'll just tie that off to 0. All right. That explains that. Oops. Oh, that's the error. OR, all right. Okay. All right, that looks better. And now I need to go ahead and put all of the default completion stuff in. So all of these request lines, that gets duplicated for CPL. All right. Let's see here. So the headers are the same, bar range, function number, those go away. And for now, we're not going to generate any of those TLPs. So that's a start. Okay. Cool. That finished, and there we go. All right. Okay, so now we're basically back to where we were before. The receive side seems to be doing what it's supposed to do. I think the only thing now that I need to do is to get the shifting correct. So let's go take a look at the test bench here. Where were we? All right, let me think if there is a way I can modify this so we can just test the right path. I'll go ahead and copy this for the time being. I'll comment this out, and so this will do the memwrite, and then we will wait. And oh, so this is doing the read here out of the device. So instead of doing that, I'm going to do await. And then skip that. Okay. Let's try that again. Okay. Wait, why is it trying to do a read? I thought I commented that out. Oh, I didn't comment it out, did I? Okay, so that ran, but it failed because I'm not looking at the header sizes properly. All right. How to fix that problem? Let's see here. So what I need to do is look at the header size bit, right? So there's a bit in the TLP header here indicating whether the header size is 3D words or 4D words. Right, so this first bit here is 3 or 4 D words header. The second one is whether or not it has data. So I need to look at, this ends up being bit 127, 126, that's bit 125. Oops, okay. Bit 125, and I need to use that to determine which portion of the data bus that I'm going to be looking at. Let me think here. In this case, I need to look at I need to add a new register. This is going to be reg. Let's see. All right, so this is looking at, I'll do that. All right, and then I also need to go down here and add this here. Okay, and moved that so this can go away, right? Clear up some space. All right, so the payload offset reg, I'm going to set that based off of the RX request header, TLP header bit 125, or actually, yeah. Well, I'll do RX st data full, and in this case, it's going to be 31, 30, 29, right? I got to go in 3 bits from the end to get this indication. All right, cool. All right, so now I need to do a conditional here. If payload offset next. Okay, so if that is set, if it's set, then I got a 4D word. If it's clear, then I got a 3D word. All right, so this is not 128 bits in this case. This is 96 bits. Okay, got to do this again down here. Get the register version of it. Okay. Okay, there we go. Tab that in, tab that in. And same thing, this is looking at 96. All right, so what I should probably do here is actually combine the writes into these FIFOs here. So instead of having it set up like this, I will do that. These go away. And that will allow me to simplify some of this stuff here. All right. So for the completion TLP during the writes, I'm going to be using request instead of the completion here. All right, cool. That's the only change I need to make. Oh, let me also get rid of all this stuff that I don't need. Okay. Okay, and then I can take this, and I can put this up here. All right. Oh, because I need the ready from the other one. All right, cool. That'll be CPL TLP ready. All right, let's try that. And there we go. So this is now doing all of the write operations with all of the various lengths and offsets. And then it failed at some point, probably because my delay is not long enough. All right, so there you go. We have one path, one of the 4 paths partially working. The completion, well, yeah, I guess I need to do a little bit of work on the completion side here. All right, so for completion TLPs, what do I need to do? I am looking at, I need to look at just the format and the type fields to determine completion versus, yeah, okay. So there's basically 4 encodings that I'm looking at here. So let's see. It's always a 3D word header. So I don't think there's actually any collisions with these bits. Is there? I'm not sure if that's the case. I don't think that's the case. So I basically just need to look at these bits to determine whether or not I have a completion TLP or not, so I can put it in the FIFO for the completions. Let me think here. So this is in terms of setting the TLP valid signals in here. I'm either setting the TLP one or the completion one. So I'm just thinking, I have this same signal in multiple places. All right, I can add an intermediate signal here somewhere. Let me think about this here. So this will be reg. All right, this one I'm going to set based on, well, let's see here. Okay, so what I'm looking at now are several different bits. I need to look at, oh, I actually need to make this a register, don't I? Because I need to remember which FIFO I'm writing into. All right, I'll deal with that down below in a minute. All right, so I get this guy. Okay, cool. Okay, let's see here. So I set the request valid. Okay, if CPL reg, or if not CPL reg, otherwise I set the okay, there we go. And I'm going to do that one more time here, and then I'm going to do it here. This one based on next. I'm going to compute that in a moment. All right, and then I need to do this. Okay, so this is going to be looking at 2 different things. The first one is I need to look at this bit clear. And then I need to look at the type field. So this is 31, 30, 29, 28, 27, 26, 25. 27, 26, 25, okay. 8 through 25 equals 4'B0101. Is that right? Yes, that should be right. And I guess I can extend this. Well, that's all right. Actually, I don't need an if statement for this, do I? Double equals. Yep. And then this, go ahead. Sign this directly. Okay. That's not going to change any behavior, I don't think, because we're not sending any completions right now. All right. Let me see if I can make this test bench pass. And then I will call it a day for today. So I'm going to set this to 1,000 nanoseconds, which is a little bit excessive, but whatever. Oh, we'll also do this for the 64-bit bar. So we'll do this for both 32 and 64, which test to make sure that both of the header size computation is working correctly. All right, so comment that out. Okay, let's see if this works. All right, so it's on length 2. Oh, that's a huge delay. So it's going a lot slower. All right, let me try if there's like an intermediate value. Maybe, I don't know, I'll try like 400. I'm going to be back in a minute. Okay, so that one actually passed. That's perfect. That means that the one of the 4 channels is working. That's good. That's very good. Let me just refresh this and we'll take a look. Yeah, so that's perfect. So you can see that the bar ID changed when it's hitting the other bar. And I don't know if that signal is up here right now. Let me see. We should also see, yep, the payload offset also changes when the bar changes as well, because it's using a larger address, which means a different TLP header size. Okay, so that looks really good. Okay, so that is the receive direction. Now the next step is to move on to the transmit direction. I guess there's still a couple of other things that I need to get cleaned up here. The back pressure I don't have currently implemented correctly, so that will be on the to-do. I'll just mark that here. To-do. Actually, I think all I need to do for this here is make sure that both of the FIFOs are ready. And then I think I need to adjust the level to less than half full so that these are actually reported with enough of a delay. Let me make sure that runs correctly. Yeah, that should be fine. Okay. All right, so that is that. Now let's see if we can make reads work. Okay, so this now requires getting the transmit direction operational. And in this case, we need to pull in 3 different inputs and merge them to generate the output. So 2 of these are going to be requests. We have read requests, we have write requests, and then we also have completions. So in order for this first test bench to run, unmodified with all those changes backed out, we need to have this working so that the completions can be sent back to the hard IP core and make their way back to the host. All right, so with this one, do we need to have 3 FIFOs? I don't think we need to have, I'm not sure if we need FIFO. Do we need FIFOs in this direction? Now, let me take a look at how the flow control works in the hard IP core on the transmit direction. All right, so this is the ready. Okay, so the application should wait at least 2 clock cycles. Oh, never mind. The ready latency is 3 core clock out HIP cycles. The interface is not strictly Avalon ST compliant. That's funny. Okay. So if RxST ready is asserted by the transaction layer on cycle n, then n plus ready latency is a read cycle during which the application layer may assert TXST valid and transfer data. They must have a timing diagram for that. Right, so if ready falls, then 3 cycles later, that has to fall. So not sure the best way to handle that, but I'm not sure if I necessarily need FIFOs at the moment in this direction, so I'm going to just get rolling with a modification of the existing ultrascale code, and we'll see how that works. So let's see, this is going to be for the, I need to do a combination of 2 things, right? This module and this one, sort of, but also simplified. Oh, I guess I am using a FIFO here. Yeah, I'm not sure how to handle the ready latency properly. But we can cross that bridge a little bit later. All right, so I'm going to go ahead, well, let's see. So this is the CC, and then there's also the RQ, and this one also has an output FIFO. Okay. Yeah, so this one has to do a lot of work because it has to adapt from the ultrascale PCIe TLP formats and whatnot. And that's not, we don't need to do that for the Intel ones because they're using basically standard TLP format. So a lot of this stuff will go away. And we also don't need to support some of these other data widths, so a lot of this stuff will go away as well. I'm actually thinking starting with this one is going to make a little bit more sense. So I'm going to go ahead and do that. We don't need that. I do need the output FIFO address width. We need sequence num mask. I'm not sure if I need those. All right, I'm going to go ahead and transfer over a couple of these parameters here. This is a TX direction. Okay, so I need that. I don't need those, I don't think. Okay. There are a couple of other things that need to be done here in terms of handing around sequence numbers. The sequence number here has to be returned here when stuff ends up in the output FIFO, which is actually not that big of a deal. And the same thing here. Read request, write request, and then the completion. Okay, cool. All right, so let's go back to this guy here. Oh, I think there was one other thing I can transfer over as well. I added this check, and I will transfer that check over there. All right, let's see now. Go ahead and transfer all of this. Same kind of idea. We'll start with all this, and we'll comment it all out, and then go from there. All right. So that's the TX read request, write request, read request, write request, and then also completion. So that, let's see. Go ahead and add some of the signals for the completions here really quick. I don't need to bother with sequence numbers for completions, only for transmit and receive requests, or the read and write requests. Okay. Okay, this is RX or RQ seek num width. We're just using transmit seek num width. All right, cool. Okay. Okay, so this is splitting up some stuff from the Xilinx IP core. I don't need to bother with that, I don't think. Let's see, idle, write header, read header. Do I need the header states? I don't think so. The header states only apply to 64-bit operations, so that means that can go away. Write header, write payload, that goes away. Okay, okay, so write request payload, but there's also a CPL payload. Okay, so I think that's what I need there. Output state idle. Let's see, so this is in terms of out data, out strobe, out EOP. Double check what those were used for. Okay, so TLP, header, data, read and write. I don't think I need those. Okay, but I do need to put together the output data path. All right. And that's going to be, you know, another FIFO. Okay, and then this is again CPL, TLP header and sideband data. Right, so this is doing the translation for ultrascale. And since we don't need to translate anything, I don't think I need any of this there, right? This is the TLP header data read. Yeah, so I can delete all of that. Okay, and that could have been a couple of these other registers I wasn't sure about, right? TLP header data. Yeah, header, so these go away because I don't need to do any translation. Okay. So here's the idle output state. Okay. And the write payload, and then I'm also going to have to add the completion payload. Okay. I will update that output FIFO in a minute. Okay, so let's see. There's several things that we need to do. We need to accept these TLPs with some priority level associated with that. I think we should probably accept the completions with the highest priority before we start issuing new traffic, new requests. All right, so this is not read request. Okay, and these are all, well, okay, that needs to be changed. Okay, there is no 64 anymore, so that goes away. Also this end here. All right, let me just go ahead and clear up all this width stuff here. That goes away as well, and 64, and also 128 goes away, because the minimum width we have is 256, so that simplifies things quite a bit. Greater than or equal to 256. So that one is always going to be true, so that goes away there. Okay, very cool. Now let me see if I can get this output FIFO operational here. All right, so the output FIFO, that's going to carry all of these signals, right? Okay, there is an error here. I don't think I have any way of indicating that in here. Right, header sequence valid, okay. Yeah, none of these have anything to do with that error signal. So that error signal is just going to be tied to 0, which simplifies things a little bit. All right, so let's see about this here. Actually, take all of these. All right. Oops, that goes away. All right, it's reg. Ready, that's going to be a wire. All right, cool. These are all int. I can go ahead and shorten this a little bit. Okay, and then that goes away there. All right, cool. And this is then going to replace all of these here. Okay. Let's bring the output FIFO back online here. All right, so these are all going to be reg. Yes, okay. Oh, right, I was going to remove error. Need valid, right? Okay. The error int, that goes away. Yes, okay. All right, let's see here. So I got all the output FIFO stuff. This all looks good here. All right, so all these, again, need to be updated based off of these guys. Right, this is going to be out FIFO. And then, oops, where did that come from? Okay. Output FIFO address with -1. Okay, there we go. And those go away. And then I need to put in a couple of these. There we go. Oh, hang on a second. Oh, I think that's, oh, okay. So we just have one segment for now, so that should be okay. All right. Did I remove something that I needed? I don't think so. Right. So one thing that's kind of unique about this FIFO is that I actually have to store the valid in it because you could have potentially more than one segment active. All right, so I'm going to go ahead then and set up the outputs here. Right. Okay, that's right. Yes. Okay. Data SOP, data SOP, valid ready error. Valid ready error. All right. So last one here, I need to do. That's just set to 0. All right. These go away. Okay, and then ready. Yeah, that's right. Okay, so this is then going to be. There we go. Okay. All right, so now the valid connections here, I need to deal with this. Valid, yep, okay. Guess I need to do this differently. If, see, EXS, oh, this doesn't work according to the AXI protocol. That's right. So I'm just going to set this to 0. I don't hold it. That's right. Okay, so that looks good. Output FIFO full, and then I have the valid int here. EXST valid int. ST valid reg. Okay. Let me see here. So this is either not valid or ready. Yeah, I guess we need a different approach for this guy here in terms of handling the ready line here. Do flow control. All right. Okay, that is going to work, I think. This is, yeah, so that one's going to have to be reworked. Okay, and then I have that. That looks good. Okay, this is not 1' B0, but I'll just set that to 0. Again, this is not. Okay. All right, making some progress here. So I just have 4 signals now that need to be passed through. Out FIFO, right? And this is int. And that one looks like that. And then over here, this is going to be out FIFO, not reg. Okay. I think I have updated this thing correctly. I could be mistaken about that though. Okay, cool. Let's see. So now I need to go ahead and drive all of these to standard values. Well, except for that one. I'll start with zeros. Okay. Let me make sure that the test bench doesn't totally blow up in my face. It did. Syntax error 185. All right. Second run. Nope. Could not find variable CPL request ready comp. All right, that's not what I want. 208. Okay, now it runs. All right. So no syntax errors so far. Or no more syntax errors anyway. All right, so I'm going to go ahead and back out all the changes I made to this. Let's go ahead and run that. So this is going to go ahead and fail almost immediately. Yep, Okay, there we go. That's what I expected. It failed with a timeout because that read didn't go through. All right, that is exactly what I expected. So let me go ahead and go into the TX path here. Okay, so I don't have any of the TX sequence numbers connection. I don't have any of the sequence numbers connected here. That's okay. Okay, so I have the TX completion header showing up. Now I need to convert that into the actual output data. All right, so go back to TX here. See here. So this is going to be for the completion here. And start of payload. All right. Okay, so this is going to be the CPL TLP ready combinatorial. All right. All right. So, I need to do something similar to what I have here. Anyway, one step at a time. Okay, so let me take a look at this here. I need to go, oh, where are the, need these signals. All right, cool. So in this case, we're going to set the data, and this is going to be coming from the CPL header. And I need to attach some of the data onto this as well. Let's see here. So I have here, okay, there's a TLP data, and this is the header data. Oh, no, I need to do a little bit more work here, right? Let's see. What I need to do is I need to go ahead and unswap the data again. All right, because this is going to be D-word swapped, so I'm going to take this, and I'm going to do exactly the same thing here. Except in this case, I'm coming from the completion headers. I'm going to txt data int. Okay, there we go. And the startup packet is set, and the valid is going to be set as well. All right. And I guess for now, I'm also going to set the end of packet. Okay, and then what I can also do after all of this is set the txt data int. Let's see, this is going to be like data width -1 all the way down to 128, and this is going to be tx cpl tlp data. Yeah, okay. All right. Let's see if that works. This is going to potentially pass a couple of tests before crashing. Yeah. That's what I was expecting. All right, so let's, if I refresh this, yep, there we go. All right, so we ran a few tests, and then as soon as the the data would, yep, so all right, I just realized what I screwed up here because I don't have that. This is just going to be 96. Okay. The completion TLPs are always 3 D-word headers and not 4. So this is going to go a little bit further before crashing. As soon as it gets up into the larger completions, eventually we're going to run into a situation where we don't transfer sufficient data. There we go. Framing error. Yep, that's exactly what I was expecting. So yeah, there we go. We're making some progress though. More completions. All right. Cool. I can now remove this. And let's see. So we've got the write payloads, and I also need the completion payloads. I'm going to reorder these. All right. So what I need to do now is get the completion payload working. All right. This is going to be, again, CPL payload and CPL payload. All right, so the way this is going to work is I need to determine whether I'm looking at the end of the frame or not to determine what to do. Okay, so this is in terms of setting the end of packet. So this one will set the end of packet. Oops. All right. There's our end of packet. We'll set the end of packet here. Okay, and then this is going to be for writing the completion payload. All right. So tx write request ELP EOP and EOP data with d words -4. Okay, that seems fine. I think is that all I need? I'm not sure. All right, so one thing that I don't need is the tkeep on the output. That goes away. Okay, so out TLP data reg. Okay, so these are set based on incoming data here. So I'm going to go ahead and put this guy right here. Yes. De-indent that. Okay, there we go. Okay, and this is going to be the completion TLP. So I save those for use down here. Okay, cool. All right, and then this one is going to be -128. All right, so this is going to be now all the same stuff to some extent here. All right, so this is going to be tx st data int. Okay. Not SOP, maybe EOP, and set the t valid. All right, cool. So this is then going to set the t valid int combinatorial ready int. All right, so this is all right, and then these again are stored. This is going to be based on the CPL TLP. And this is setting tx st eop int. Okay. And that's either going to go to idle or the CPL payload. All right. Let's run that and see if that gets any further along. Oh, all right. So we got up to some point where it timed out. It's definitely run further, but then something went wrong. What happened? It timed out when it was performing what operation? Let's see, memory read, the memory read, memory write. Where is the operation that it's doing here? I'm just trying to figure out how big it is. Oh, here we go. Oh, this says, all right, so this is 32-bit bar, length 30, offset 3. Length 30, offset 3. Okay. And the previous one that worked is what? Length 30, offset 2. And the error that we ran into was timeout. So it was attempting to read, but I guess it didn't get all of the completions. All right. Let's see here. So we have TX, CPL, TLP ready. Where's the valid? So this is still high. All right, so that got stuck high. Why did it get stuck high? TLP output state. Next, it did go into state 1. But it did not leave this state for some reason. All right, so TX write request TLP valid. Oh. Well, I am not supposed to be looking at write requests, am I? And I also have the same problem here. All right, let's try that one more time. And it failed. Let's see. So this failed with an assertion error. So something got screwed up in terms of how stuff was passed through. See here. Wait, did it fail at the same point? Memory operation 32-bit bar, length 30, offset 3. Okay, so there is some problem here then. 1B, 1C, 0 instead of 1B, 1C, 1D. So either it didn't get written correctly. Let's see here. So the completion here, BC. Let's try to check to see if it equals the test data. So, so there's one completion. Then there should be a subsequent completion, right? Is that how it, I think that's how it works, right? So there's one completion, and then there should be a second completion, maybe. All right, let's see what was issued originally. So, receive TLP, there's one TLP, there's two, no, okay, so one TLP here, receive, this is going all the way through 1D000, okay. Right, okay, that looks correct. Okay, and then later on it tries to perform the read, right? So it sends that, and then it sends a second TLP here for a read request. All right, that's a single D word read. And then later on, I should have another read operation. So there's the single D word read going through here, right? Okay, TXRX sending upstream. Okay. Where does it issue the next operation here? Okay, here's a mem read with first BE8, last BE1, and length 9. All right, so that should be the actual read operation in that case. All right, so the original write operation had length what? Leave TLP. Where is the length field? Length 9. Yeah, okay, so length 9 should be correct anyway. All right, got downstream TLP. Length 9, okay. Oh, I think I know what the problem is. I got this -4 in here. I think this should be a -3. I think it is cutting off the last D word and not realizing there's another cycle there. Nope, didn't like that either. Unless I need to go the other way. I don't think that's the case though, right? Because it should be, well, let me think here. This is taking the strobe, I'm shifting it by, actually maybe I just want to shift this by 3. One of these questions, are you shifting to the left or are you shifting to the right, you know, and by how many? All right, so in this case, I'm looking to see if I have anything that's set that wouldn't have been transferred in that cycle. So this is kind of looking at the remainder, right? So in the first cycle, you transfer 3 D words of the header plus however much payload that you have. Well, up to a full cycle. No, it didn't like that either. Right, so you're transferring that up to a full cycle. So if you have 8 cycles per transfer and the first 3 contain headers, then you can contain up to 5 D words of data in that same cycle, which means if it was a full cycle coming in, then you might have to store 3 D words, you know, for the next cycle. So what this is checking is to see if okay, yeah, so that's okay. Well, I think I had it right previously, because what I'm trying to do is see if those upper 3 lanes are set. So shift it by the number of D words, that would give you 0, but I want to check the upper 3 lanes. Yeah, okay. So that should be correct. All right. This is the kind of stuff you run into all the time with this sort of thing, is trying to get all the little corner cases sorted out and get all the conditions correct. All right, let me just take a look at this trace and see exactly what's going on. So we get in on the input side here. Here is the CPL data. All right. A, B, C, D, what? That does not make sense. This makes sense here, right? 1, 2, 3, 4, 5, 6, A, B. Oh, no, this is fine. Yeah. Okay. So the A, B, C are just not used. So it's just the 1D that needs to be transferred. And this 1D is not getting cycled through, right? So in this case, where is the strobe input here? LP, okay, strobe is set to 1, right? Because we have this lower D word that needs to be transferred. But for some reason, it's detecting the end of the transfer too early. All right, so this is what's coming in, and the state that I'm in, TLP output state. So at this point, I'm in this state, and the TX CPL TLP is valid, right? Yes, it is. And out TLP EOP reg should be low. Out TLP EOP reg is low, yes, because I haven't stored that yet. And TXST ready int, that's also true, yes. So I set ST valid, yes, okay. So all this is taking place correctly, and the only issue is down here at the bottom. So, oh. So that's not being included in the ST data int for some reason. All right. Because this should be CPL. Nope. I thought I got rid of all those. I guess I missed one. All right. Yeah, so it was sending a 0 instead of the data byte that it was looking for. Looks like this might actually run to completion. Maybe. I hope it does. That would be good if it did. Because then the next step is to get the DMA working. Which, considering I've been making pretty good progress here, that I don't think will be all that much more complicated on top of what I have implemented right now. Yeah, okay. Hey, there you go. So reads and writes are now working. MMIO should work. The next step then is to implement the DMA operations. Alrighty then. So let's go back to here. And I'm going to turn the memory operations off. I'm going to turn DMA operations on. And then I guess we can see what happens. Let me think about this now. All right. Move this wider interface thing. So for the DMA operations, what we need to be able to do is pass through the read and write request operations. All right, for the read requests, we shouldn't need to do anything special. For the write requests, we're going to have to do something kind of similar to what's going on with the completions here in terms of passing through the data. All right. So that one's going back to idle. I'm accepting that. All right, and then I need to do all of this, except not from the completion packet. In this case, we're going to be pulling this from the TX read request here. And the rest of these, I will just set this all to 0. All right, so this is 128. And this is 64, no, 0 to 31. And this is 127 to 96. Okay. And then all of this go away here. Okay, there we go. I do stop and EOP, pass it straight through. Okay, very cool. All right, so that would be the deal for the read requests. Well, let's go ahead and run the test bench with the DMA tests and see how quickly it fails. All right, yeah, so it tries length 0, offset 0. It sends the TX frame out of the generic interface, and then, yeah, it gets stuck. Okay. Memory operation DMA, I think this is for a write, so that would explain why. Let's see here. If I go to DMA operations, yeah, the first one is testdev.dma memwrite. So yeah, okay, that would explain why that didn't work, because I haven't implemented that piece yet. All right. So in this case, we're basically doing the same thing as the completions, except now I get to flip all this back, right? TX EPL. This then becomes write request. Write request. Okay. However, we potentially have to shift things. See here. Same thing as before, right? It's a question of, are we doing a 3D word or a 4D word header? Right, so this one starts at a 128. Right. Okay, where was that? This is a payload offset next. Add that register here. This is in terms of the TX write request. X write request. PLP header, and it's 127.65. 125, right? Yes, this will be 127, 126, 125. Yes. All right. So that is payload offset. Now I need to add the actual register for this. Goes up here somewhere. Okay, and then I also need to pass this through here. Yeah, I'll actually move this down. Okay, there we go. And then I need to set it down here. All right, there is a payload offset. Payload offset next. Do one or the other depending. And then I guess I need to do one more thing down here too, right? I need to change how I'm shifting this thing. Let's see here. Okay, so if the payload offset, if that's clear, then it's a 3 D word header, otherwise it's 4. Okay. Go ahead and copy this guy, and this will be for the write request. And again, I need to go through and replace all the completions for write requests. Okay, that looks better. Then I need to pull this as well. Well, actually, not quite. Okay, so this one I need to output one offset or the other depending. It's going to be based on payload offset reg. Okay, and again, same thing down here. And if that is set, then this becomes -4. Okay, I guess I need to think about the conditionals here, but this will work for the time being. It's 4, and this one is 3. Okay, cool. Okay, and then I need to transfer this guy down as well. So this is actually the off case, and then when it's set, then I need to do 128. I think that's right. Maybe. Maybe. Okay. How badly is this going to blow up in my face now? All right. It got a little further along, I think. Did a couple of things, and then again failed on, well, I guess the question is, did this return the wrong data, or did it not write the data correctly? Okay, what happened here? This is memory operation DMA length 2 offset 0. Okay, so it sent that. There's your data, right? So we have a 1 byte that's non-zero. It performs the write, and it performs a read immediately. Except that's a totally different address. Let me think about this one here. Memory read, so why would this address be so different? So when we get this here, so this, what was the address for this original thing, right? So offset is 0. Well, it shouldn't be, or the address should not be 0, I don't think. Oh, this starts out PCIe IF frame, converts into H-tile PCIe frame. And then this one has the address of 0x100. All right, well, let's see here. That's 61030. Oh, is that what's going on here? I may have a test bench issue, possibly. So the deal is I have a small optimization for the, yep. I have an optimization here for the ultrascale devices where I just force all of the addresses that's generated by all the PCIe components to 64 bits, because that's how they pack into the Xilinx PCIe, TLPs. So forcing everything to 64 bits just makes the logic a lot easier because you don't need to check. You just always generate 64 bits. Okay, I don't know if that solved anything. But yeah, so we don't need that for the Intel parts. Okay, so I think this failed in the same spot. Yeah, okay, here we go. Memory operation, DMA length 2, offset 0. Yeah, so it looks like the address should be all 0, but for some reason in the H-tile frame, when it interprets that, it's getting a different address, right? Yeah, it's seeing address of 100 and data of all zeros. So yeah, that's not right. Let's see here. 1, 2, 3, 4. Yeah, so what's going on here? What we should be seeing is a 3D word header. Well, hang on. So 6. So what would that be? So 6 is 4 set and 2 set, which would be a mem right. But that shouldn't be a 64-bit. That shouldn't have a 64-bit address attached to that, should it? Seeing all zeros here. Well, all right, hang on a second. Let me figure out what's going on in the test bench here. What operations should we be generating here? All right, so for DMA, take membase plus offset. And offset, well, I think we were starting with 0 for the offset, yeah. And membase, that is something that we allocated, right? We allocated a small region here. I think that got allocated at address 0. I'm not 100% sure, but I think that might have been what happened. Yeah, so we fire off enumerate here. So MSI is not configured, so this one will be allocated starting at address 0. So yeah, this should end up being 0. Yeah, so the address should be 0. But the question is, why is this H-tile frame being, no, this is not quite right? Because we have 1, 2, 3 D words of header, here's your data, and then we have this extra D word here. All right, I think that may be an interface issue in the test bench. Let's see here. Not the file I wanted to open up. There we go. All right. Interface. So how does this do the packing then? Well, actually, yeah, that's still generated as 6. So actually, well, it's still a test bench issue because it shouldn't be generating this with the 4D words. Actually, that issue may be on the other end. Where is this guy? PCIe. This one is a little bit of a mess, but let me see here. So there should be 464-bit address. Yeah, so that's that's used when it's generating the PCIe IF frames. I don't think I set that anywhere else, right? That was just set here and I removed that. That's perplexing why it's generating that the frame with a 64-bit address. So PCIe IF frame from TLP, or wait, yeah, from TLP, there we go, 464-bit address. Oh. Well, that's silly. So the frame data, where is it handling the header here? Oh, I see. This is a 464-bit address, but I forgot to actually take this into consideration. Oops. All right. Okay. Well, that was a bug. I'm not sure if that affects anything here. That still failed. All right. Okay. So it didn't extract the, let's see here. The TX frame, that looks correct now. So we have the data, we have the payload. All right. But the RX frame here, which is the H-tile PCIe frame, doesn't have the data in it. It's just all 0. All right, so let's take a look at the latest packet that came in. Let's see. Most recent TX write request. There we go. Yep, so there's the data. But when it output this, well, let's follow through here. So this is coming in, and then so we accept that, and then we should be outputting, where is this here? st data int. I mean, I think that's the output data there. So the problem with using these really wide numbers is it's not necessarily clear where this is right in the middle of it. So that is bit 136. So bit 128, 0, 1, 2, 3, 4, 5, 6, 7. So that is correct. All right, so then this looks like it may be an issue with fixed force 64-bit address field. If header 0 in 2 or 62. Oh, but this is going to be on the other side, not on the generic interface side, but on the H-tile side. Right, because I should have address 0, but then this one should be data. All right, so over to the H-tile model code here. Actually, probably the H-tile interface code on the sync side. All right, let me think here. So I pull out that, and then I pull out the D word count. Right, so that should, well, I mean, if I'm getting the D word count wrong, then that would be the problem. Header, this is sample data. Okay, so that should be, so 31, 30, 29. Yeah, that should be extracting those first 3 bits. All right, where is this extracting the actual data? Data equals sample data. All right, mins 32K. K is coming from, oh, this is the K here. All right, so min self.seg byte lanes D word count. Oh, unless I'm shifting to the wrong spot. That may actually be the problem. Okay, let me take another look at this then. TX, this is the, well, what is the issue here now? So I've performed the write, and this is an issue on the read. So this is on the, the completion data is getting garbled coming back, which is going to be in the receive direction. And here, so this has, yeah, so I have the CPL data coming out here. Input state idle, input state payload. This is checking to see if we have the completion, right? And based on the offset, then we're going to take either one offset or the other. And this should be doing exactly the same thing. Well, no, sorry, this is on the RX side or on the TX side? Well, the other issue could be that the write is not being shifted correctly and it ended up writing all zeros. Is that what happened? Actually, I guess that makes more sense then, right? Yeah, so this is the write request, and then it wrote all zeros. Okay, that's what happened. I've been thinking about the wrong side here. Okay, so this is on the TX side in terms of the write being shifted the wrong way. And I think that was the issue. I think I just had those two mixed up. Well, I think it seems to be working this time around. I'll give it a couple more minutes here, but that's pretty good progress so far. All right, let's a cleanup here that needs to be done. Oh, I need to do the sequence numbers. Uh-oh. And something is not happy. Let's see here. So this tried to do what? Tried to do another memory read. Or DMA length 30 offset 2. Oh, DMA length 30 offset 3. So there's your TX frame going out, but it doesn't make it out. Okay, so what happened here? Alrighty then. Yeah, this one didn't time out for some reason. I guess I have the test bench set up a little bit differently. Okay, so the input here, yeah, right request TLP valid is just high. So for some reason that one didn't get, accepted. Did that not happen? That's going to be down here at the right payload. So right payload, that one is relevant. TXST ready int. Yep, that's high. And right request TLP valid. Right request TLP valid is high. Okay. TXST valid int. TXST valid low. Oh, well, it gets set on this cycle here, but that's interesting, but it doesn't clear out that. What is going on here then? Because I thought this was the same thing that I had in terms of issuing these guys. So let's see. All right, so let's see. This case, ST valid is being set, and in this case, it is the one gets set out TLP data next, out TLP EOP next, right? Out TLP EOP is just low. What? What is going on here? So it's getting stuck in this state for some reason. Where does it have the TLP output state? Yep, it is stuck in that state. Does set TXST valid to 1. What prompted that to happen? There's a TLP data. There's also a TLP. There should be a TX write request TLP probe, right? Yeah, okay, so that's one. Because I still have this one little straggling byte at the end of it. Why is it being stuck? What is going on here? Not hitting any of these here. Oh. I need to be transitioning to the correct state. Okay, there we go. Now that it's in the right state, maybe it'll work. All right. I don't know if it's... Oh, hey, there we go. DMA test passed. Yes. All right. Now, the last thing that I need to do is to actually get the sequence numbers forwarded properly. This is not really a big deal. I just need to add a couple of registers here for the sequence numbers. Oh, I actually don't even... There's a bunch of stuff that I don't need here. What is this? Need that. I don't need that either. Got all those. I got all of these. All right. Now, what I do need is some registers for passing the sequence numbers back through. So these are going to be associated with these guys here. So let's see here. I make a copy of these. I don't need that. Sequence numbers are used by the DMA engine to determine when a request has actually hit the wire. And this is very important so that you issue things like events and interrupts only when the state is going to be consistent. Okay. And I also need to assign these. Let me go ahead and take care of these registers real quick here. Okay. Oh, actually, what I'm going to do, set all these just to 0. Yep, okay. And then down here, same thing. And for write request as well. Okay, cool. Make sure all of the outputs are reset properly. Okay. All right. So let's see, I got those, and then I need to go ahead and add the assigns. Oops, that's assign. Wrong key. Okay. That goes away, and then what I need to do is, let's see here. All right, so for read requests, this comes from txrd request TLP SEQ. That is set high there. All right, very cool. And then I do this one more time here. And this is going to be for the write requests here. Okay. All right, very cool. Now what I need to do is go back and turn on all of the tests that I had here. So I'm going to do both of these. Make sure the DMA stuff looks good. And I don't think the current setup in the test bench is generating sequence numbers. But these should at least be all 0. And we should have, yeah, there we go. Yep, we have the valid indications indicating that these operations have taken place. All right, that's perfect. Okay, and then I will run this again with those other tests enabled as well. So this will run all the read tests and all the write tests. Yeah, I was thinking that these interface modules were going to be a lot more complicated to write, but it looks like I managed to get both of these working today. So that's pretty darn good. That's better progress than I was anticipating. Now, in terms of actually running this on the FPGA, I think I'm probably going to have to pack it in for the time being, and we'll pick it up tomorrow and see if it works. Let's see this test bench finish, though. Yeah, I guess there's still a couple of other straggling things to take care of, primarily in terms of flow control. Yeah, okay, there we go. It passed. Yes, all right. So that means MMIO works and DMA works, although we are still waiting on a couple of other bits of functionality. So that is the whole test running there. We're looking at the TX side. That looks pretty good. So we can see, let's see, this first round is sending completions right up until here, and then it switches to sending read requests and write requests. That looks pretty good. And if I switch over to the RX side, we see kind of the same thing, where this first part is going to be sending requests. Let's see, RX request. Yeah, right, yeah. So these are requests that are coming in, and then these are completions that are coming in as prompted by the DMA engine. So yeah, that's looking pretty good. Now, so there's still a few signals that are not connected here in terms of flow control and whatnot, so I'll have to get some of that squared away. I think, yeah, so I guess not all of these signals are going to be present. So credits limit, yeah. Some of these are going to be slightly longer term to figure out all of the implications and connections and remapping and whatnot. But at least in terms of the core TX and RX paths, it seems to be working. As you can see, we got it to the point where this test bench passes. So the next step is to actually connect this up to the PCI Express hard IP core and see if it works. And let's see, is there much we can do in that direction tonight? I guess there's a couple of things that I could do. So we've got, for the PCI Express code, I've been working on kind of a common example design setup. So this is kind of the core logic, and then I have a PCIe wrapper with the PCIe DMA engines. And then I have an ultrascale wrapper and an H-tile wrapper. So these bring in that kind of interface shim layer. So what we can take a look is see if I can get the H-tile one, operational here. So let's see what we can accomplish. All right, so we got the TLP segment count, TLP seg data width, strobe width, header width. I think these are all correct. Yeah. Okay. All of these are the internal connections. And if I go down here, this is the connection through to the main core logic. So TLP seg count, TLP sequence number, PCIe tag width, read op table size, op table size, read TX limit, read TX FC enable. All right, so I need to set this one to 0, and I guess we check the bus number. I think we do. All right. We got the bar size settings. Okay. All right, so then we need to pull in the H-tile interface here. So we take a look at the interface here. Make sure I have all of the correct parameters. All right, let's see here. So I got MSI count, MSI enable. I don't need those. TX sequence number count and width. The header. Okay, these all look fine. Okay, this is RQ sequence number width. Don't have that. We don't have any of these. All right. All right. So there's segment count, segment data width, segment empty width. All right, and then TLP seg count. All right, that looks a little better. All right, cool. All right, so then the next step is I need to go ahead and connect all of this stuff that's going to the PCIe hard IP core on the H-tile. So let's go take a look at this. We'll go ahead and grab, well, I don't have that many connections at the moment. This is fine. These just get passed straight through pretty much. All right, cool. Okay. Move all of that. Now the question is Ford going to be happy with this? Let me go ahead and just pick off the analysis and synthesis portion of it and see if it complains about any syntax errors. I'll go ahead and start putting the interface together here. All right. All right, something was not happy. All right, let's see what the problem is here. Okay, CFG max read request and CFG max payload. Okay, that's right. Yeah, so with the Xilinx devices, those come in from the top level, but those are not the case here. max payload size, and max read request size. Okay, X tag enable. Okay. Run that again. Okay, so while that's doing its thing, I'm going to finish updating all of this stuff here. Oops. All right. Let's see. So I think let's go through all of these here. All right, so this is not necessarily finalized. Some of these are definitely going to need to be changed a little bit. But what I am going to do real quick is add a bunch of connections at the top. That'll be wired in. All right, so I'll go ahead and take all of that. Don't need to be input or output, just wires. Okay. All right. Let's start hooking stuff up here. CLCFG func, CLCFG add, CLCFG roll. All right. Oh, the RX buffer limit stuff. That is a different story. I think that's. I leave that here. Now I remove it from here. Okay, so that needs to go away over here too because there is no RX buffer limit stuff. Okay, that looks good. I'll go over here. Again, Quartus was unhappy about something. Still complaining about that? What? Maybe I named it wrong. Let me see here. Yeah. Max read request size and max payload size. There we go. Okay. Okay, so those are those three. Now I have the TX credits. TX credits. Oh wait, that's not implemented totally either. All right, so I'm gonna forget about that one. Get rid of all these comments that are not really helping much of anything here. Okay, RX connections. RXST ready. RXST stop. RXST EOP. RXST data. RXST valid. RXST empty. TXST SOP. TXST EOP. TXST data. TXST valid. Okay, TXST error. TXST ready. TXST bar, oops. Oh, RXST bar range. Okay. Wait, does this indicate what the function number? Oh, I think the function number, maybe I just need to tie those to 0. So VF active 0, function number is 0, VF number is 0, RX TLP abort. Oh, that, was there a signal for that? I guess not. Let's see, was that even present here? I did have a connection for RX TLP abort. Well, I'll remove that one later. Okay, so those all look good, and those are all there. All right, let me go ahead and make the connections down here. There's no RX. EX, that's not correct yet. I will fix that up later. Okay. All right, let's see here. Need to add some parameters. Big count is 1. Big data width is 256. This is log 2 of seg data width over 32. Okay, so those are the first couple there. All right, tag count 256, that's fine. Okay, well, I'll just make these 64 for now. And I can just comment out all of these to use the default values. All right, so TX and RX FC enable is 0. Sequence number enable is 0. Well, I guess I can turn on the sequence number. I think that's implemented. I don't have the flow control implemented for now. Okay. Is that everything? I'm not sure. Let's go for broke. This could take a few minutes. I think it took about 20 minutes to synthesize with just the hard IP form. Oh, clock and reset don't have drivers. Oops. Let me deal with that then. Okay, let's see here. I need to connect this to core clock out hip. All right, there's one. And then a reset. I'm going to take reset status. I think that is the inverted version of reset status. Let me double check with this thing in terms of the resets. So reset status active, high reset status. Oh, so that's actually just fine then. Okay. Same functionality as reset status, core ready when asserted indicates that the, oh, that's the wrong one. PLD clock in use, same effect as reset status. Okay. Active high, that's a normal reset connection. All right. I guess that'll work then. Very cool. All right, so let's try this one more time. That I have the clock and resets connected. Did I connect those here? Yes, I did. Okay. Okay. And I guess that means that I can clean up a little bit in the PCIe hard IP core simulation model. Let me take a look at this here. H-tile model, let me take a look at the reset code here. Search the reset, and then when it comes out of reset, it sets that low. Yeah, okay, that looks good. All right, so this one, I think we're okay here then. When I run the tests, I'm waiting for falling edge reset status, so that's perfect. Okay. And I can do the same thing over here too. Where was that test bench? Here it is. Okay. So I can go up and I can connect the reset status to oops .rst. Okay, and then I don't need to touch. Where was that? I did that. Fine. I think that's what it's looked like before. Okay, same thing here. All right. Oh, I guess I do usually have a delay after that. All right, so let's go ahead and leave the delay in. What I do need to do is make sure. Oh, yeah. All right. What happened? Oh, PCIe H-tile config. All right, I don't have that added, so I need to add a new file. The project file. Let's see here. Project add remove. There we go. Okay, cool. /RTL. Oh, sorry, no, lib PCIe RTL. Come on, Quartus. All right, I'll come back to that in a minute. Oh, start. Okay. Now Quartus is running. All right. Let me see here. What was I doing? All right, I was fixing up these reset connections here, and then I needed to go change something in the H-tile model to make sure that things don't blow up in my face here. All right, cool. So that one is that, and then this is CLR, and this is PLD's clock in use. Okay. Okay. Reset status. Oh, that wasn't what I wanted to do. This was going to be PLD clock in use. All right. Where was that test bench again? Let's run that and make sure it doesn't blow up in my face. Okay, that's working. All right, very cool. Okay, so this is now running in Quartus, and we'll have to see how long this takes to finish here. Hasn't failed on something yet. Well, no major errors so far. It looks like it's definitely gone beyond all of the standard syntax error and whatnot. All the files seem to be there. Synthesize some nodes away. Well, I guess we'll see. "57 device resources after synthesis." Right, something does not seem right here. Always got to take a look at the warnings. It's entirely possible that I've either forgotten to connect something or I've connected something up incorrectly. Well, not sure. I'm just going to let it run, and we'll see what the numbers look like. Actually, I guess we want people to look at a more detailed view here somewhere. Just trying to see if this has any information in terms of just overall resource consumption. Oh, okay, this is actually inferring a decent number of logic elements here. So we've got, let's see, this is the core H-tile instance, there's the core inst. Yeah, so that's 15,000 ALMs, that's 16,000 ALMs. That's not bad. Block memory bits, 740 kilobits. Most of them in the AXI RAM, and a whole bunch in the DMA RAM. So that seems about right. Well, we'll have to see. Some of this stuff could be ending up in block RAMs where it shouldn't be. Although I'm not sure if block memory bits is including distributed RAM or not. Potentially this early in the process, it doesn't have a good indication of that. Well, while this is running, I'm going to see if I can put together a test bench for just this example design. I guess I didn't quite set this up the way I was planning on doing that, but that's okay. All right, so that's that. And then I can go into, let's see. You just take that whole shebang and then simplify it. Let's see, how did I do this for one of the other example designs? If I go take a look at this one. Okay, I just had the top level settings there. So just those three. Works fine. All right, cool. Have clock and reset. Have the connections to PCIe. I'll go ahead and remove. Well, this one is not right. I'll have to bring that one back later. Okay. All right, so now what I need to do is go into test bench directory here and update that to use the H-tile model. All right, there we go. There's that, and now I have the H-tile model here that I use for testing this, and I'm basically going to do the same thing. So that comes in and it replaces ultra scale stuff here. That. And that goes away. Okay, and let's see. We go ahead and bring this over. Have all of this stuff connected here. Okay, so there's RST and clock. That looks fine. PCIe generation 3 link with 8 and clock frequency 50. All right. All of that can go away at this point. That connection is made there. All right. Then I think the rest of this is all basically correct. Well, okay. I need to go ahead and fix the make file now. I'll fix up this Python stuff later. Need to open up the test make file and point all of this at the p-tile stuff here. P-tile, or not p-tile, h-tile. All right, so I have Rx and TX and the CFG, and the MSI will come later. And I'm just going to comment out the module parameter stuff for now. Let's see how badly this complains. Oh, all right. I have a typo. Oops. Tile has an E at the end. All right. Sample core PCIe H-tile. All right, so I think I have an extra argument in here somewhere. Right, I did uncomment some stuff. Maybe I was a little bit overzealous with that. Oh, all right, so I think I have a couple of signal width problems. This is going to be FPGA core, the funcnum, that should be 2. Yes, all right. And then I think I also need to change that on exactly what happened there. All right, so also need to change the sample design top for the H-tile to have the correct function number width here. That should be 2. All right. config function 1 and 2.1. All right, and I also need to make that change here. 131. And it failed for some reason. All right. So the DMA didn't work. All right. What? Be building with waveforms enabled. And it didn't for some reason. I comment out something. Oh, I did comment out some stuff that I didn't want to. All right. I comment out this and that, and we'll try this one more time. Okay, do I have a wave dump this time? Yes, I do. Okay, so let's try and figure out what happened here. So it does test DMA. Right, so let's see here, test DMA, and then these should be memory. What are we going to be doing? We're going to be doing memory reads and then memory writes. So it sets everything up. Oh, I see a PCIe DMA start read. There's the reads. But I don't see anything after that. what is going on here? Potentially, I don't have a signal that needs to be connected, wired up properly. Okay, I think I know what's going on. I need a bus number. Yep, so I need to pass that out, and I'm going to go ahead and stop Quartus because it's definitely not going to work without that. Wire 7 to 0 bus num. And this also needs to get passed out of this. All right, so that's going to be, where is that? Tile IF, yeah, all right, here we go. Oh, I do have a bus num output. I just didn't connect it. Well then. Let's try that again. And now it passes. All right, very cool. Let's restart Quartus and see if it'll build correctly. So yeah, there we go. We can walk through exactly what happens in this test. First, it performs a write and then a read against bar 2. These are just a couple of quick test operations. So it does a write, and then it does a oh, right, okay, so it does a write, and then a read, and then there's a completion that comes back, and that was the data that it read. Okay, it didn't read 0, so that's good. It's supposed to be hex 11223344, but, you know, most of those correspond to actual ASCII characters, so they show up like that. Okay, and then it does test DMA. It does a bunch of register writes to set up a bunch of things. And then here is the PCIe DMA engine saying, oops, I got an operation to perform. So it generates 2 read request TLPs. You can see with different addresses, and then there should also be different tags. This tag 0 is tag 1. Here we go, memory read tag 0, memory read tag 1. So there are the 2 read operations. And then here are the completion TLPs, which contain data being handed back to the PCIe hard IP core. Or no, getting handed back to the design as if it's coming from the PCIe hard IP core. And then we read the status register, and then we do the same thing in the other direction. So this does a PCIe read to go from the host to the card, and then it takes the data from the card and it writes it back to the host. So we can see PCIe DMA start write, and then it generates a bunch of frames going back, and then the memory writes of that data being written out into the host memory. And then it reads the register again, indicating that it's finished, and there you go. So that ran. So that ran using the Stratix 10 models. So now the question is, and the shims that I just put together, now the question is this going to work in the hardware? And unfortunately, we're going to have to wait for Quartus to do its thing. Step away for a couple of minutes and let Quartus grind away on this. I thought I was going to have to do multiple parts here. I guess we'll have to see if this works, right? If it doesn't work, then we'll have to pick up the debugging tomorrow. If this does work, then this will wrap it up. Well, there's still some other odds and ends that need to be squared away, but that's going to require some additional work. Anyway, it looks like synthesis completed, so no syntax errors. Now it's going to try running the rest of the tools here. The fitter, which does the planning, placement, routing, and timing, and then it will generate the configuration file for the FPGA. We'll drop it on and see if it works. Anyway, I'll be back in a few minutes. All right, well, while I'm waiting for this to run, I'm going to take a look at what the story is with flow control on this sucker. Because there is a question in both the receive and the transmit direction about how you do flow control properly. I think this one doesn't have any flow control in the receive direction, which is slightly annoying, but I guess there's not much that can be done about that. You just gotta deal with the stuff as it comes in. There's a TX credit interface in terms of transmitting stuff, and it's definitely important to respect the transmit credit counts, because otherwise you can run into all sorts of weird issues with headline blocking. PCI Express uses link layer packets to transfer flow control credits, so that the transmitters don't send more packets than there is buffer space available at the other end of the link. So transmitting packets consumes flow control credits, and then whatever device at the other end will then release those flow control credits once the operation has completed sufficiently, basically. So, for example, if you have a PCIe switch, when the packet is forwarded, then it will release the flow control credits. Right, so on this device, there are several different ports for the flow control credits. And you have to keep track of how many credits you've used and how many credits have been released. So with the Xilinx devices, you can actually look at whatever credit counter you want. And there's basically 6 different types of credits. There's posted, non-posted, and completion. And then for each type, there's header and data. So a header credit is basically one packet. And then the data credit is, I want to say every 16 bytes. Going to be one credit. It's 4 aligned D words, something like that. Yeah. Right. So flow control credit interface, there are connections for kind of the main types. There's the posted header, the posted data. So these would be used for writes, or write requests. There's the non-posted header, non-posted data. These are used for read requests and atomic operations and things like that. Read requests don't have any data associated. I/O operations, atomic operations, and configuration operations do have data attached, and those are all non-posted. So non-posted means you're going to get a response back. Right, so header credit, so net value. Yeah, I need to figure out exactly where this is coming from. Where exactly it's measured in the setup. I have a block diagram for this. Now they have a block diagram for the update loop, but I'm not seeing anything indicating exactly what these correspond to. So the TX credit interface reports the number of flow control credits available. Right, the following equation defines the available buffer space at the link partner. It's Rx buffer space equals credit limit minus credits consumed plus released credits, where credits consumed equals credits consumed application plus credits consumed PCIe IP core. IP core consumes a small number of posted credits for the following reasons: to send completion TLPs for configuration requests, so there's only going to be a couple of those, and not particularly often, and to transmit posted TLPs for error and interrupt messages. Every time there's an interrupt, then it will consume a posted TLP. Posted TLP header credit, and I guess also a data, because those are writes. The hard IP core does not report the internally consumed credits to the application. Without knowing the hard IP core's internal usage, the application cannot maintain a completely accurate count of posted or completion credits. They don't really say much about how you're supposed to compute this, do they? Okay, refer to the TX credit adjustment sample code for code that calculates the number of non-posted credits available to the application. RTL recovers the updated flow control credits from the remote link. It drives the value of the link's partner's RX buffer space for non-posted header and data credits on the TX NPH credits and TX and P credits, respectively. All right, so how does this work? So they have non-posted header credits consumed, TX credits type, NPH, oh, non-posted header credits limit. Oh, that's the output. All right. Okay, so credit consume 1, credit consume 2. Okay, so that's just a delayed version of this. And this is looking at the credits type, so it's either, well, so if the type is 2'B01, then it passes it through, otherwise it's 0. I don't know why they delay that, but they do. Okay, then 3R, PH, credit consume 2R. TX, PH credits. So this is just passing through this value from the core. That doesn't make any sense. I'm going to have to put the logic analyzer on that to figure out what in the heck is going on. Ah, man. Yeah, the issue is there's a couple of different ways that the core can report the credit count that's available. So on Xilinx FPGAs, you can kind of pick what you want to see. And they give you an option of, well, I have the data sheet over here somewhere, I think, right? There we go. Yes. All right. So where is the flow control? Here we go. Flow control. Yeah. Okay. So there is an input here where you can select what kind of credits you want to use, or what credits you want to see. You can see transmit credits available, transmit credits limit, and transmit credits consumed. And the way this works is, I want to say available is kind of the difference between the limit and the consumed. So the consumed increments as you send stuff, the limit increments as the link partner releases credits. So you take the difference between these two to get the available. The issue with the Stratix 10 stuff is that I think they are only reporting this limit value. So that means this value is going to be going up as whatever is at the other end of the link releases credits, which is, you know, kind of the most important thing to know. And this one doesn't start at 0. This will start at some fixed value. But the problem is that you don't know how many credits the IP core itself has consumed. You can keep track of how many credits you've consumed in the DMA engine or whatever. That's not really a big deal. You just do that based on the number of packets and the size of the packets. But yeah, the bigger problem is computing this if you don't have a reliable number for the credits consumed. So that one I'm going to have to do some thinking about and probably do some experimenting. And I'm definitely going to have to connect up the logic analyzer to see what in the heck these credit outputs are doing. Otherwise, I can't really do much. But yeah, part of the idea here is that you shouldn't have to bother with the core deasserting the ready on the transmit side, because you're never going to try to hand off an outgoing TLP if you don't have credit to send it. Although I guess maybe that doesn't guarantee that the core is not going to have any issues. Well, okay, so what could potentially cause problems? MSI, maybe. Those have to be sent somehow. Those are going to be slipstreamed in by the core, basically. The MSI is one thing that needs to be done. What else is there? MSI, and then potentially configuration requests, right? Those are going to be sending anything that the core has to send and consume credits. Could potentially block the interface. Unless the core is sending it at a lower priority level and just holds off until it's idle, which I would say that's probably not necessarily ideal, but would work. I'm not sure how they implement it though. And then the other potential thing is link layer traffic, but I think the link layer traffic should be sent basically at a lower priority level than the actual packet traffic. And if you run out of flow control credits because you haven't been getting link layer traffic that's freeing credits, then that's a self-correcting problem. Because if you don't have credits, then you can't send anything, and then the credits will be released. Yeah. Yeah, so for that one, it's not particularly clear what the solution is going to be until I have this thing running on the FPGA and can put a logic analyzer on there. I won't have a good idea of how to handle flow control properly. If there's anything else here that needs to be dealt with, I think everything else is pretty straightforward. Oh, I guess one thing that I can work on while Fortis is running, still running, it hasn't crashed yet. I can start putting together the interrupt shim, the MSI shim for the Stratix 10 devices. So what I'm going to do here is for the H-tile, I got the H-tile CFG. I'm going to do the US MSI, the H-tile, SI.p. All right, cool. Go ahead and open file, H-tile MSI. All right. All right, so MSI IRQ coming in, and then what were those connections on the other side? I think I can pull those out of this guy here. All right, let me see. Big configuration interface tile. All right, there we go. Yeah, I guess one thing I don't have set up with this MSI shim is really any way to, use any other reset connections, or any other, not reset connections, but any other physical functions. It's just hardwired to 0. Whatever, that can be dealt with later. All right, so let's see here. These are all out. And then this one is in. Okay, so this is, let's see, so if not active reg, what's the story with active reg? How does active reg get cleared? Active reg gets, I sent or I fail. All right, so this is waiting for MSI int app MSI ACK. Yes, okay. Okay. And I basically, all of these need to be outputs except for ACK. PC is 0. This is IR. Second. So MSI int reg. Okay. So MSI int reg. What am I doing with this MSI int reg? That is used. That's not used anywhere. All right, cool. So that's fine. It'll be 4 to 0. All right, cool. All right, so that means all this stuff gets to go away. I think. All right. Not sure if that'll work. I'll have to test that a little later. Making progress. It's taken a lot longer than it did before. I think last time it took 22 minutes or something to run the whole thing, and it's at 23 or 24 minutes, and it's still in the middle of routing, so. Oh, we'll see. Let's see, was there anything else to take a look at here? Interrupts. Oh, right, I was going to take a look at status. Is there any way of indicating what the, pending interrupts are? Application layer request, traffic class, MSI number, rolling legacy interrupts, function number requesting MSI. Yeah, okay, so, Oh, it says routing is done. On retime. 99% on retime. Well, I guess the other question, not so much is it going to blow up and is it going to run, but is it going to close timing? We'll see about that. I think we may need to do a little bit of optimizing to make it work correctly on the Stratix 10 device. We'll see. Clock domain, okay, so there's several different clocks here. This one says insufficient registers. Well, I guess we'll have to see. Okay, so this is showing some of the logic resource utilization here. Everything is quite low, which is good. Oh, this is a routing interconnect usage. I see. All right, here we go. Let's take a look at the resource consumption. Logic utilization, yeah, 2%. Well, that's good. That should be small. Total labs, memory labs. Okay, that's weird. I'm gonna have to take a look at that because I'm expecting it to use more of, oh, actually, I think it's using a lot more M20Ks than it should be. So the M20K is the Intel equivalent of, the block RAM, basically. And the memory lab, that's the equivalent of the, distributed RAM. So I may need to take a look at, it's like all of these FIFOs and whatnot should all be sitting in the M labs, not in M20K. So 169 M20Ks seems to me like it's way too much. Looks like it didn't put anything in M labs. So, It's using 3 megabits of block RAM. I mean, some of these things definitely need to end up in block RAM, but there's a lot of stuff that should be implemented in M labs. Well, I'm going to have to take a look at exactly what's going on there, because that does not make sense. Potentially something about how I'm using the RAM elements here is making Quartus unhappy. Oof. Oh, all right. That's not good. Yeah, I'm gonna have to take a look then. What is failed by 1 nanosecond. Total endpoint -30. 186. All right. Well, we got some work to do apparently. What is this anyway? All right. So this is. Oh, that's the. Can I open this up? It can give me more detail. Yeah, so this is using Altera Sync RAM, which is not what I wanted, I don't think. Well, all right, so what are we doing here? This is so out completion FIFO, RX completion PLP header. That's on the RX side. All right, now it's opening the timing analyzer. Okay, that'll probably give us some more details of what's going on there. And again, it takes like 10 minutes to load stuff. My. All right. Port setup summary. What I'm looking at, right? I guess I need to do some poking around in here to generate some other reports. All right. Yeah, I think I'm going to have to figure out why this is generating M20Ks instead of MLabs. And I'm not sure what else I'm going to have to do here. Like PCIe tag table RAM. What are these associated with? Combinatorial cell. I think there's some stuff in the PCIe DMA components somewhere that Fortis is not happy with in terms of how I'm trying to infer some of these distributed RAMs. So yeah, I think if I can sort that out in a way that it works on both the Intel devices and the Xilinx devices, then that would maybe improve the timing a little. I'm just trying to figure out exactly what this path is here. So this is coming out of the DCM. Okay, this is the clock path. Right, that's the clock path, and we get to the data path. All right, so yeah, so that's coming out of the RAM block. Cell doesn't even say what the cell is. EC. Sure. Then it goes through a bunch of combinatorial cells. But I'm not sure what these cells are because it's just saying data F comb out, data F comb out. So that doesn't really help very much. PCIe tag table RAM address. The C out, C in, sum out. So that looks like it's feeding into a adder of some sort, and this ends up running into address delay reg 13. This is all in DMA IF PCIe int. DMA IF PCIe. Wait, which one? Read. Yes. Okay. So this is ending up in. This ends up in address delay reg. All right. Well, where is the next being set from? So that is coming from. That's a good question. What sets this? Oh, here it is. Yeah, okay. So that comes out of, yeah, okay. So I take the PCIe tag next from the header. I do a lookup in the RAM, and this should be a distributed RAM, so this should be a really fast lookup, and then we get the address. But it seems to be using an M20K. Yeah. All right, well, this I think is going to be a problem for another day, trying to get to the bottom of this and figuring out why Quartus Prime is inferring the wrong components here and coming up with the proper solution to fix that that's going to work for both the Intel devices and Xilinx devices. So at this point, the test benches work. I think we'll have to pick this up maybe tomorrow then, if I can come up with some, some reasoning behind this or some particular paths forward to try to improve the situation. All right. Well, if anybody has any questions or anything, fire away. Otherwise, I think I'm going to be closing this down pretty soon, and I guess probably picking it up tomorrow sometime to see if we can actually make this run. No questions? All right, well, I guess I will go ahead and close this down. Thanks to everybody who tuned in. We made a lot more progress today than I was originally planning. I wasn't expecting to get all of the test benches to run. I thought that was going to take, another day's worth of work. So at this point, we got some timing issues to figure out, and hopefully that's not going to be a gigantic pain in the rear. All right, so at this point, I'm going to go ahead and sign off, and I'll definitely post if there's going to be a follow-up. All right, well, signing off.